extend a warm and heartfelt welcome to the esteemed dignitaries, distinguished speakers, and all the participants, both present here and attending online, and my dear faculty members. It gives me an immense pleasure to welcome you all to the National Workshop on Use of Machine Learning Tools and Artificial Intelligence for Effective New Drug Discovery and Development, organized by Amity Institute of Pharmacy in association with Amity Center for Artificial Intelligence. It is my privilege to welcome our keynote speaker, Dr. Shiv Prakash Ratnam Sir, CEO, Apiquel Pharmachem LLP, Ahmedabad, and President of the Indian Pharmacological Society. Distinguished speakers, Professor Ravi Shankar Ramachandran Sir, Chairperson and Chief Scientist of the Biochemistry and Structural Biology Division at CSIR, Central Drug Research Institute, Lucknow. Dr. Firoz Khan Sir, Senior Principal Scientist, CSIR, Central Institute of Medicinal and Aromatic Plants, Lucknow. Professor M.K. Datta Sir, Additional Pro Vice Chancellor, Dean Student Research and Director, Amity Center for Artificial Intelligence, Noida. Professor Tanveer Navid Sir, Deputy Dean, Health and Allied Sciences, Amity University, Noida. Professor Hevagiri R. Chitmay Sir, Head of the Institute, Amity Institute of Pharmacy, Noida. All the participants and my dear colleagues, आप सभी का हार्दिक स्वागत, वंदन और अभिनंदन. In today's fast-changing world of drug discovery, artificial intelligence and machine learning are proving to be powerful tools. This workshop brings together brilliant minds to explore how cutting-edge technologies like machine learning and AI are revolutionizing the landscape of pharmaceutical research and drug development. This workshop has been carefully planned to give you practical experience and expert insight on how these technologies can help make drug development process faster, smarter, and more accurate. To formally commence today's workshop, I now invite Professor H.R. Chitme Sir to deliver the welcome address. Welcome, sir.
Thank you, ma'am. Good morning to all of you. Pujaniya Founder President, sir, Most Honorable Chancellor, sir, Honorable Vice Chancellor, Madam, Honorable Additional Pro Vice Chancellor, Professor M.K. Datta, sir, Professor Tanveer Navid, sir, Deputy Dean Health and the Allied Health Sciences, my dear colleagues, Dr. Rajiv Kharab, and my dear friends also, and all those who have joined online for this workshop. So today's event is one of the important event because it is a workshop. It's a hands-on workshop also. In the first half, we have the lecture series, and the second half, we have the hands-on experience activities. The first half will be in the J1307, and the second half will be conducted at the Amity Center for Artificial Intelligence. So it is an amalgam of both of them. So the one is the lecture and followed by the hands-on experience. So, so this is we in the long back, so we started having the curriculum which is called as a computer-aided drug design. The computer-aided drug design, so where we used to use the software like the Schrodinger and Autodoc and others. So that is also the kind of the system which we use. And by using those systems, so we were able to predict the binding affinity, efficacy, the site of action, and then the route of elimination and all those things. So that is how the drug delivery and the drug discovery process has started and it has been expedited. And now, so the software what we are using, so that is an important one, but now there is a change in the trend. And that change in the trend is with respect to the AI and ML. This is the era of artificial intelligence and as well as the machine learning. So where the Chinese people are using this AI and ML extensively and finding out the molecules in a better way. So, before this workshop, we also conducted one workshop on the network pharmacology. And in the network pharmacology, we studied that, so how to use the network pharmacology in the drug discovery and development process. Now, this is an extension of the previous the workshop which we have conducted. And I'm sure so this will be the value addition to the network pharmacology workshop. And the workshop is being the concepted by our Professor Sir M.K. Datta sir, the additional pro-vice chancellor. So he asked us to conduct the A and ML based drug discovery process workshop. So which will be hands-on, and I'm very grateful to him. So for giving this opportunity to conduct this workshop and giving us the other speakers also. So today we have the Dr. Shiv Prakash Ratnam sir as a keynote speaker. I welcome you, sir, to this workshop. I also welcome Dr. R. Ravishankar ji. So he is the scientist in CDRI. Then we also have the eminent speaker, Dr. Firoz Khan, so who is from the CMAP Lucknow campus. And we also have Dr. Rakesh Chandra Joshi. So here, Dr. Rakesh Chandra Joshi is our in-house speaker. So he will be conducting this session in the second half and as well as the hands-on experience also. So I take this opportunity on the behalf of our founder president, sir, the chancellor, sir, and as well as vice chancellor, madam, and the additional pro vice chancellor, sir, to welcome all the speakers for this today's workshop, and also welcome the online participants and as well as the offline participants for this workshop. I'm sure so when you attend this workshop, so you'll be learning more about the A and ML based systems. So because A and ML based systems are revolutionizing, as Dr. Alka has mentioned, it is revolutionizing the drug discovery process. And it is not only with the drug discovery and development process, but also in the clinical trials also. If you see the clinical trials earlier, the statistical test, which statistical test to be applied, so we were under the confusion. But now the AI is helping us in finding out the better statistical test to be applied and what should be sample size, that is the sample size calculation, safety of the drug, and efficacy of the drug. And if you remember, there is one AI tool called as AlphaFold. And this AlphaFold is the device which has been used to predict the structure of the COVID-19. And based on the structure of the COVID-19, we were able to generate the antibodies for these COVID-19. And we also use the benevolent AI. So this benevolent AI is also an AI tool, so which is used for the repurposing of the medicine. That is how the remdesivir and all of them, they come into the picture. So especially, so if you see baricitinib is one of the anti-rheumatoid arthritic drug which was reprocessed for the COVID-19. So these AI tools have helped us to understand the structure of the COVID-19 and then try to find out the some medicine which are already there as an antiviral drugs, anti-arthritic drugs. Even we use the tocilizumab also during the COVID-19. It is also based on these AI tools. So the COVID-19, of course, we always say the adversities always brings an opportunity. And the COVID-19 was an adverse event which has happened in a once in a century, and similarly to the other events also. But this time, so the COVID-19 has made us to think how to expedite the process of developing the vaccines and as well as finding out the new molecules in a better way, safer, and as well as effective. So I'm sure so this workshop will help you to understand the things much more and also learn more of the things from the our own expert. If so, yesterday there was the admission career counseling session where our founder president has mentioned Dr. M.K. Datta is the one of the finest AI scientist in the India, and there is no doubt. There is no doubt. Yeah, so it is endorsed by our founder president, sir. And fortunately, we have Dr. M.K. Datta, sir, himself in the event as a guide, as well as a mentor, and the chief guest also for this function. So I welcome all of you to this session, and I'm sure so you'll enjoy this session. Thank you so much. Thank you.
Thank you so much, sir, for your warm and insightful welcome. We are honored to have with us Professor M.K. Datta, sir, Additional Pro Vice Chancellor, Dean of Student Research, and Director of Amity Center for Artificial Intelligence. He holds a PhD in computer science and engineering and has served in key academic and research leadership roles, including Dean at AKTU and Director of the Center for Advanced Studies, Lucknow. He is currently a visiting professor at Brno University of Technology, Czech Republic, and has been recognized among the top 2% most influential scientists globally in the field of artificial intelligence. May I now invite Sir to share his opening remarks on AI introduction and application. Welcome, sir.
Okay, so good morning to all of you. I think whoever present offline in the room and online presents also. So good morning and welcome to this important workshop. First of all, I would like to thank Professor Chitme and Professor Tanveer, Naved, and all other faculty for the organizing people who conducted this important workshop. And because currently a lot of AI things are happening, and as she already mentioned, ma'am has already mentioned that I'm basically an AI scientist. Like basically, I'm a computer scientist for the last 10 years. I'm into AI, so I have seen the journey. You know how AI has come up. My papers, if you see my papers, they're from 2011, 12, where AI was not a boom. I mean, it was like just as a routine subject. So then came 2014, 15, 16, 17, 18, and we saw things happening in a very disruptive manner. So the purpose of this PPT is a little bit taking you through a little bit of AI. I'm not a pharmacy scientist, or I'm not a clinical person, but I have been associated with certain people with whom I have been dealing with some AI applications. Maybe a couple of things I'd like to show you, and I'll take you through, just tell you where we are at this moment, and how AI has been proved to be so much disruptive, in its interesting journey. I always start my presentation with this slide. I ask you, if I want the machine to differentiate between elephants and dogs, how can you do it? It's very simple. Put x-axis as the x-axis as the weight, y-axis as the height. Then you dot the points. Height, when weight, elephants will form a cluster. The dogs will form a cluster. You form a boundary, and all of a sudden you see it's interestingly divided. So anything below the boundary is a dog. Anything above the boundary is an elephant. So very simple. Height, weight, two factors. Everything is done. So you can distinguish between dogs and elephants. The problem comes when I give you 100 categories of butterfly, or 100 categories of snakes, or 100 categories of fishes, because geometrically, texture, statistical features, or if you take any texture features, color features, the geometrical aperture, I mean, you can take anything, and all of a sudden you see it's so difficult for a machine to differentiate between 100 categories of snakes or butterfly or fishes, because snakes almost they carry on the same. But if you understand, let's say I'm a person, I have spent 45 years of my life in doing so many things. Now I have experience. I can look into some of the fishes. I don't know, आप लोगों में से कोई बंगाली है यहाँ पे? Is there any Bong? No? So if you ask, then they will say what is a rohu fish and a katla fish and another chingri fish and there's a illich fish. There are 100 categories of fishes, and still we know this is a fish, although they look very similar. I am a Bong. So, but now you want the machine to do the same kind of thing, which the fishes apparently looks to be very similar. What do? No mathematical logic, no maths, no logic, no mathematical model, no logical model can hold. And all of a sudden you say, define a term called as machine learning. You have to make the machine intelligent and make the machine think like human beings. And this is where I introduce the term machine learning. Okay. This slide is actually important. So I would like to tell you about this. I'll just tell you the summary of this slide. Had you been a computer science, I think my audience is only pharmacy people, so I will not get into too much of thing. Had it been a computer science students over here or faculty, I would have spent at least 10 minutes on this slide. But with you people, I'll spend a couple of minutes tell you. See, AI was always there. 1954, there was Arthur Samuel. So there are many people. In 2024, the Nobel laureate is Geoffrey Hinton. Are you aware of it? The guy who got Nobel Prize in 2024 in physics, his name is Geoffrey Hinton, and he's the father of modern AI. Whatever AI business we are doing currently, this came from Geoffrey Hinton. But interestingly, Geoffrey Hinton gave the theory in 1974. There's a concept of backpropagation, which is based on differential calculus, which was given in 1974, for which he got the Nobel Prize in 2024, 50 years later. Okay, there are some reasons I'll try to. Now, what I say is that, see, if you ask me during my PhD days, when I did my maybe 2005 and, long back, so 20 years back. So those days we were into supervised learning. Some, I don't know, the computer science people will recognize 20 years back when I'm during my PhD days, I used to do support vector machine, then naive Bayes, random forest, do manual engineering of features and train models and etc. etc. The journey continued, came 2010s. Okay, deep learning came into picture. Deep learning is a very powerful thing where they extract the features from the data itself, no manual feature engineering. It's started in deep learning, then transfer learning, etc., etc. And then comes the most decisive year of 2017. In 2017, there is a company called Google DeepMind. I don't know if you've heard about it. Google, one of the finest, brains they pick in that Google DeepMind, and they work in US. They came up with a research paper in 2017, December, called as Attention is All You Need. And it caught the attention of the world in 2018 and 19. And in 2018, when this paper came up, this model came up, we call it as transformer model or the attention model. AI became 5,000 or 20,000 times more powerful. If you understand, AI was traveling a journey from, let's say 1990. AI was slowly going like this. It was just increasing in a linear way. Slowly, it was increasing, LSTM, GRU, so many things were happening. The context memory was becoming 20 to 25, 30. We were having a gradual change and comes to 2018 and it becomes infinite. Do you understand the curve? It was just like this. And in 2018, it became infinite. So the power of AI becomes 2000. If you look into this, I said 2018 is modern AI. There's a transformer model called as, there's a model called as transformer, which is based on attention model. And from 2018, the power of AI is unlimited, limitless, infinite, whatever you say. The game changed. There's a model called as transformer. Now, when I say AI is infinitely power, or when AI is power with limitless power, there must be some catches. There must be some bottlenecks. So what are the bottlenecks? The bottlenecks are how much compute power you have. I mean, how much supercomputing facility you have, how much data you have to train. So if you see the big players in US like Meta, OpenAI, Meta, Google, they all have pumped in a lot of money. In fact, billions and trillions of dollars have been pumped in. And the game changed. So you have to understand, 2018, the model is called as transformer model. There is a concept called as attention network. I don't want to explain all these things, for computer science students, I would have explained. And it became changed 2018 onwards, and today we are sitting in 2025. So these 7 years have changed the world. There's a guy, I'll a little bit tell you about Hinton. I think I don't have that slide here. Hinton, what he said, the person who actually invented this AI business, backpropagation, Geoffrey Hinton. Please remember this name, Geoffrey Hinton. He got Nobel Prize last year. He quit Google. He used to work for University of Toronto and Google part-time. Okay, he quit Google in 2023. And when he quit Google, he was addressing the US media. And in that media, that's a long interview. You can do Google Browse and see his exit interview when he was quitting Google. Two important things you can decode from his interview. Number one, he regrets creating this neural net. The man who did all AI business, to a certain extent, he regrets, why did I do that? You can decode, you can see the interview yourself and you can decode. And the second thing important in that interview, when he was addressing the US media, he says that what he expected 30 to 40 years to take place. He expected these neural nets to, become a very superpower and disruptive technology within 30 to 40 years. It actually happened in 3 to 4 years, which was beyond his expectation. He said that he thought that it will take 2 or 3 decades for this technology to mature and become disruptive. And he says, I no longer think like that. What he expected 30 years to take, it happened in 5 years. So these are the two important, things that the man who himself, gave this AI. I'll skip all these slides. These are not for you. They're not for you. I'll take a moment here. Now, I try to relate this. Please understand. Now, what is this multimodal AI? Now, for example, I'll relate a situation. I see, let us say, I see Professor Chitme. He's sitting in front of me, and you give me a task. You write a paragraph on Professor Chitme. So what I will do, I'll look at him. I'll say he's wearing a Professor Chitme is wearing a white shirt. He's wearing a blue tie. He's wearing a black specs. He has black hair. He has, he's wearing a gray color pant. I am seeing, you understand? I'm looking at him and I'm making a note. I'm trying to relate something. Please understand. So I'm looking at Professor Chitme and I have written, he's wearing white shirt. He's wearing blue tie. He's having a I card. He's having black hair. He's in this. Some five lines or 10 lines I've written about him. Now, in the process, this is what I'm trying to relate, the analogy of neural nets with actual neurons. So here now, what happens, the three things which are actually playing. One is my vision sensor, my eyes. Through my eyes, I'm looking at him and seeing that he's wearing a white shirt and he's wearing a blue tie and etc. etc. This is my vision sensor which is fired. Okay, one. Second is my mouth. My mouth is trained. See, my eyes are trained to look into this and identify whether it's a white shirt or a black shirt or whether it's a blue tie or a red tie. My eyes are trained. Okay. My mouth is trained to speak. I'm speaking. The Professor Chitme is wearing a white shirt. I'm making a sequence of sentences. I'm making a sequence of words, framing sentences, and giving some outputs. And in between my eyes and my mouth, there is a portion of my brain called as the visual cortex, which is responsible. Once again, my visual cortex is also trained to interconnect my mouth with the eyes. Did you understand? There are three parameters. There are three functions happening simultaneously. My eye, I'll call it now in computer language. What I'll do, I'll say my eyes as a vision sensor. There are many vision models that have come up. ResNet, Inception, vision transformers, so many things. So I'll relate my eyes as a trainable neural net, as a trainable neural network. My eyes are trained. Let us say I show you a donkey or a monkey or a cow or a dog, you will say this is a cow. But all of a sudden I bring a new animal which you have never seen in your life and I say, oh, tell me what is this? You cannot tell because you're not trained for that, right? So my eyes are trained to distinguish what is the color of his shirt and what is the color of his eye. My visual cortex, visual cortex is a part of the brain, I think many of you must be knowing, which is actually responsible for, converting the neuron pattern that generates. Billions of neurons are generated from my retina that go to the visual cortex and I decode it as whatever I'm seeing. And that interconnects with my mouth. And my mouth has been the visual cortex, the interconnect between my mouth and my, now I relate it. My eyes can be replaced as the vision sensors, the vision models. There is a big branch of computer science called as computer vision. All of you know this, computer vision. So my eyes is a computer vision model. My mouth is the LLM. ChatGPT is an LLM. DeepSeek is an LLM. Gemini is an LLM, right? Llama 4 is an LLM. So my mouth is an LLM. Relatively, when I'm a human being, my mouth is trained to speak, give me output, I'm talking. ChatGPT is also trained. And the interconnect, the visual cortex is an interconnect. It's a mid-level connect. Sorry, it's a mid-level connect between my mouth and my eyes. So what I'll do is that my eyes, I'll train it for a computer model, I'll train it with a vision sensor. My mouth, I'll train it with the LLM and the interconnect with. So 3 neural nets being trained separately for solving 3 different tasks can replace the human system. So this is how, I'm trying to relate. I'm not going to do too much. I'll skip these slides. Yeah, this is important actually. Here, what I say here, what I say, I mentioned that Arthur Samuel was 1954. Geoffrey Hinton in 1974, stochastic gradient descent was in 1960s. So the basic ingredients of all the deep learning and generative AI were 50, 60, 70 years back. The question is, why Gen AI now? Why deep learning right now? There are 3 important reasons. Number one, you must be, let me tell you that any deep learning or Gen AI models are data hungry models. They need a lot of data to train. So first, number one, you have got huge data space and currently you have got drives and distributed networks. Even our phones have become, if you go back, let's say, if you go back some 15 years back, we used to have some MB of this one. In our phone, we used to have MB 15, 20 years back. Today, we are having TBs and GBs, right? So huge data availability for training. Hardware, companies like NVIDIA has come up with CUDA models. Sequential model has been transformed into pattern. I'll tell you how. For example, there's a small kid. A small kid. Now, when you train a kid to differentiate between dogs, elephants, cats, he does it one by one. First, he sees what's a cat, then a dog, then an elephant, then a donkey, and a monkey. And the process continues in a sequential manner. 15 years back, 20 years back, our models were sequential. One by one, the model is to learn based on features. Today, you bring 1,000 labels, 1,000 different categories and pumping the model. There is massive parallelization available, which will train the model parallelly. Okay, the models like CUDA have come up. And third is software. That's a good news for non-AI domain scientists. The good news is you need not be a fine Python programmer. You need not have extraordinary good skills of Python to train your models. That's a very good news for at least for you, faculty and students of pharmacy. Even if you do not know, see, I'll tell you the example. My first PhD student in 2013, yeah, my first PhD student some 10, 12 years back, she was working on an optimizer problem. Okay, now she's in US, Arshdeep Kaur. She's in US right now. She's in some good university in US. To write the optimizer is, some differential calculus and gradient calculation, some mathematical interpretation has to be done with the Python. She wrote a 250 or 300 line code to implement an optimizer. Optimizer is, a training pace controllability in a deep neural network. 250 lines. Can you imagine? It will take more than a month. So all the mathematical things you have to write and the code and debug and a lot of errors and so many problems. Today, if you want to do an optimizer, you write one single line, pull a command from a Keras library. So that much ease you are at. Today, if you want to do and there are so many optimizers, there is Adam, there is Aragrade, there is RMSProp, there is Delta, there's so many, the flexibility, the variability, the advantages of using the latest technologies are so much available. If you use a model like PyTorch, have you heard anyone have heard about PyTorch or TensorFlow? So these are libraries given, you just need to pull one single line command and you can get it done. So 10 years back, you used to line 300 lines of code. Today, it's a single line code. So softwares are available. You do not need to be a extreme. I'll skip all this slide. Now I'll come to something called as generative AI. This is interesting. I think all of you have heard about Gen AI, generative AI. This is interesting. Now, what is the difference between generative AI and the normal AI? Generative AI comes from 2018. The term generative AI comes from the transformer model itself. Okay, 2018 and onwards. So prior to 2018, AI was what you can say, it's a task solver. AI was a task solver till before 2018. I mean, task solver means you can make a classification task, a regression task, an object detection task, a biometric face recognition task. You can give the task to AI and the AI will solve a task for you. You can train it for that. Okay, it cannot generate instances on its own. But comes 2018, the transformer model, okay, and AI becomes generative. Now, what is generative? Generative is something where it can create new instances. Well, I'll explain. If I ask you this question, which face seems to be real? Anyone can guess? A, B, or C? Huh? What if I say you all three are fake? Okay, all these three faces are fake. Now, how we have created this face, maybe. Okay, before I go to here, I'll try to explain. Let's say, you'll understand how it works and why is it looking so much real. I'll give a funny example. Let's say I want to make a supermodel to do an advertisement for my jewelry. Let's say I have a garment shop. I have a sari company. I am a salwar suit company or a sari company or an ornament company. I need a supermodel, a beautiful, pretty looking model to promote it. So I don't know currently who are the supermodels. In our time, when I was students and all, there was Madhuri Dixit and Aishwarya Rai, and there were some Deepika Padukone and all these people. Now, if I hire Madhuri Dixit or this Aishwarya Rai, I have to pay some 20 lakh rupees or some 15 lakh rupees, and then there will be a cameraman, there will be a boss, there will be a driver. There will be so many things. There will be a makeup man, there's a hairdresser, and you can estimate the cost and the photographer and so many things, and maybe the cost will go for 50 lakh rupees. I don't know, maybe 20 lakh rupees, something. And 2 days of pura tamjham and shots and all these things. And finally, you are done. Now, what I'll do with the Gen AI, please try to understand the concept. You'll understand. Please understand, and I want you to understand generative AI. What I'll do, I'll pick all the most, popular 50 top models of the country. Aishwarya Rai and Madhuri Dixit and all, Deepika Padukone and whoever. I'll call it as a latent space. I'll make a latent space. All these, this people I'm mentioning is a point in that latent space. I've pulled them in a latent space. And from the latent space, I'll generate new instances. I'll generate a fake instant, a new instance, which will have the eyes of Aishwarya Rai, the lip contour of Madhuri Dixit, the face of Deepika Padukone, the hair of some X and Y and Z. Finally, what is happening, when I'm picking a fake instance, when I'm picking a new instance from the latent space, the low level features, let me explain. You made a face, I call it as a high level feature. My lip contour is a mid level feature. My nose is a mid level feature. My eye, like my lip contour is a mid level feature. My jawline is a mid level feature. Or iske beech mein chale jaoge, jaise let's say if inside my eye the points and the dots and the pixels and the edges and the corners are low level features. So what I have done is that the low level features and the mid level features I have picked from real instances to make a new instance. Did you understand? So all of a sudden, what you see is that there is a new face generated. Now, if you look into this face, it is generated from a latent space. I don't know whether you'll understand. Most of you may not understand. Latent space is like, let's say I ऐसा करता हूँ, इस class में let us say there are how many? There are let's say 25 or 30 or 40 people sitting. I'll take photograph of all 40 people. I'll dump it in a latent space. Okay. And then I'll generate an instance where eyes, I'll pick her, nose, I will pick yours, I'll pick all these things. And finally, I will generate something which has been generated from real low level and mid level features. Did you understand what I'm saying? And that's generative. Okay, I'll show you this. Now, this slide may become a little bit more interesting for. Now, look into this. There are some birds. And the birds, you will see there's a pose, there is a texture, there is a background, and there is a shape. And the bottommost portion, what you can see here is that I have interchanged each of them. I have interchanged them. Can you see? I have interchanged the pose and the texture and the background and the shape. And all of a sudden, I have generated some new instances. But interestingly, these new instances will look very much real because the background is real taken from somewhere else. Okay, the pose is real taken from somewhere else. So real instances, low level and mid level features being picked to form new instances and hence the term called generative. You are generating new instances. Okay, let me proceed. I think this is the GIF you can see. I think this GIF will run. You can see the moment I change the background, you see the water background. So I'm interchanging things. I'm playing with things. Okay, the deep fake comes from here. Anyway, now this is how, this generative models works like this. Horses can be converted. This is a cycle gun, actually. I teach when my students, I call it a cycle gun. The zebras are converted into horses and the horses are converted into zebras. Look into the source and destination. The low-level features are maintained to give you a destination where the low-level and mid-level features of the source is retained in the destination. Can you see this? The face and the top and the lip contour. See, this is how, generative AI models can actually work. It has learned the low-level and the mid-level features of your face. I'll skip this slide. Yeah, this is interesting. Now I talk about creative imagination. Okay. Have you heard of Stable Diffusion? How many of you have generated images with GPT or DeepSeek or Gemini? Okay. There's a model called Stable Diffusion. So what I have done here is that I've given a very much nonsense command. You can see the command is absolutely nonsense. I'm asking the AI model to, what is that? The prompt is make an image of a soccer player riding a tiger near a sea beach during sunset. So actually this means nothing. If I go to the finest painter of Delhi, if I go to the finest painter of Noida and ask, okay, now give me a painting, a soccer player riding a tiger and in sunset and all these things, he will find this is nonsense. I mean, he cannot actually imagine this. See, human creativity is based on imagination, some creativity, some emotions, okay, some humanly feelings. On, let's say, a painter can, now if you go to a painter and talk something, realistic, a beautiful girl with long hair standing in the mountain and looking for something, he can actually visualize this because that's realistic. Okay, you can say a man walking in the market and something, then he can, this is something which a painter cannot actually visualize. Okay, and most likely the human intelligence and the human creativity may not return you a unrealistic, because this is nonsense, this is unrealistic. Now I have given this command to Stable Diffusion, and Stable Diffusion has given me this image. Now this image is fairly good enough. You can see there is a soccer player who is riding a tiger, and there is a beach and there is a sunset. Almost all the prompt, whatever I have asked, it has made, right? And it takes around maybe 15 seconds. It's a Stable Diffusion model. Now, I would like to make a difference here. You need to understand. Here I always tell people that artificial intelligence in itself is a misnomer. It's a wrong term. Wrong term means anything which is artificial cannot be intelligent. Okay, artificial intelligence in itself is wrong. Anything which is artificial cannot be intelligence is only with human beings. Although I am an AI scientist, but I'll tell you how it works. When I have given this prompt, there are 80 billion mathematical operations which has taken place, and the image is returned. It is pure mathematics. Do you think your GPT has some intelligence? Do you think your GPT has emotions? Do you think your GPT has creativity? Do you think your GPT has got some creative imagination? No. GPT is a 70 billion, GPT-4 is a 70 billion parameter model, which effectively means when you have given the command, there are 70 billion neurons where gradient calculations means linear algebra operations, matrix operations, and some gradient differential calculus operations are happening, and you get this image. And that's it. It's purely mathematical. So there's no concept of creative imagination. There's no concept of, human creativity or human feelings. So it has made it. Okay, so this is, but interesting point is, this is where we are in the AI this AI space. We are at a position where AI can act. This is stable diffusion model. This feature is available in GPT-4. You can try. Any one of you have tried? No? Nobody? Nobody. Oh, surprising. You can try. This feature is available in GPT-4. Okay. Now, the same story, what I did is that I took Llama 3. Llama 3 is also a LLM model. So I took the Llama 3, I put this photo, and I asked Llama 3 to describe the image. So it has described it. The morning I was in the 15 minutes back, I was explaining about Professor Chitme that I am looking at him and I'm writing some description. So this is the same story. It writes that image is a vivid, semi-realistic digital painting of a soccer player. It has generated a complete description for you. Now look in the same story, the way I was mentioning. So the vision sensor has fired with a neural net. Okay. So the LLM has fired. It's just like if I ask you this, if I show you any one of you this photograph and tell you describe this photograph, you'll also start writing. Na? I see a soccer player who is riding a tiger. There is a sea beach. There is a sunset. Something you'll write. The same story going on. Okay, the neural net, the vision sensor has been activated. It has understood, decoded. The vision language has been activated to understand the language, and then the LLM has been activated, to generate the response. And there's a mid-level connect between these two sensors. Ideally, all these three are trainable parameters. I mean, trainable neural networks. So this is cross-domain translations. Zebras to horses, horses to zebra. If I give you a photograph, this is the picture of summer. This is how Switzerland, Zurich will look in summer. How will it look in winter? GenAI already knows. It will give it to you like that, Face generation. Yeah, MOE is another interesting concept. I think all of you have heard around, maybe around 3 months back, China was making a lot of noise. There was one Chinese LLM that came in the market called as DeepSeek, and all the US big players like OpenAI and Meta, they actually we saw a huge downfall in their market share. 7%. They lost 7% of their revenue within one day. The DeepSeek was released. What is this DeepSeek so specialized? Not sure if you'll understand, but still I'll try. Let's say there's a 70 billion parameter model. Now, when I say 70 billion parameter model, when I give a prompt to solve, 70 billion operations happens. And carrying out 70 billion operations at the backend of a GPU of Sam Altman. Sam Altman is the CEO of this one, of OpenAI, is a massive computational cost. The GPUs are melting when we are playing with when we are playing with this ChatGPT in our offices. You must remember, and let us be responsible not to misuse this GPT, because every command you execute, you're costing the environment. Maybe every command is equivalent to 1.5 liters of water required to cool the GPUs, which are placed somewhere in US. Your every command, for fun also we write, okay, GPT, tell me what is this, some nonsense we write. That is costing you 1.5 liters of water, which is a limited resource. It is adding to the, anyway. Now let me come back to this Chinese product. Now this Chinese product, it created a concept called, mixture of experts. What it did, let us say my brain has got 70 billion neurons. Human brains has 86 billion neurons, 86 billion. Now, GPT-4, 70 billion neurons, every operation, 70 billion operations will happen to return you the output. Now, this innovation of this Chinese company was, they call it as mixture of experts. The last layer before the softmax function, there is a layer where they have divided the entire neural net into subnets. Let us say there is 70 billion neural net, 70 billion parameters. So 10 billion for maths, 10 billion for emotions, 10 billion for logic, 10 billion for some philosophy, 10 billion for, it has divided some, I call it as experts. Now, what will happen? The softmax function can read your prompt and activate only one of the mixture. So as a result, what is happening is that, let us say if there is a 70 billion parameter and you have got 7 experts or 10 experts, to every command you are using only 1/10 of the resources. So that's a huge, cost saving and computational cost saving. And that's how these Chinese people had made a huge impact on that. I'll skip all these slides. Maybe if I see something. Okay, I'll stop here. Look into the level of intelligence. I call it as multimodal AI. I'm giving, this is a stable diffusion model. I have given this photograph to this model and I'm asking this model, tell me the recipe of these biscuits. Okay, these cookies. Now, please understand, even if I show you this and ask you what is the recipe, so how much intelligence you need? The first thing is that the vision sensor has to be activated. The vision sensor has to be activated to understand whether it's a maida or a atta or whether it's a chocolate or what is that? Is it cocoa or what is that like? This is point number one. And then somewhere in your neural net, in your brain, if you know how biscuits are made, that portion of the information has to be retrieved and produced and given it as a return of the prompt. Now, this is how multimodal AI. Now, please understand, for example, LLMs. For example, LLMs like GPT-4 or DeepSeek, or Llama 3, they are trained with almost whatever is available in the internet. For example, GPT-4. GPT-4 knows everything what is in open source. Do you know this? जो भी आपके open source में, whatever is available in open source, including, many research papers and review papers, GPT-4 has already read it. So it already knows how cookies are made. So the vision sensor has only to fire and look into this and understand what is this cookies, like whether it is maida, whether it is chocolate. So if you can understand, it goes back to the relevant portion of the context memory where this information is stored and can return. This is interesting, actually. This is the Clip OpenAI model. So what it does, for example, if I show you, if I show you this mobile phone and I tell you this is a mobile phone, it has got 64 GBs of 64 GB RAM and it has got 5 GB of memory and it has got a 20 megapixel camera. I'm showing you a mobile phone and I'm giving you some texts. So your mind is processing with 2 inputs. You are looking at an image, your vision sensors are fired. Are you able to understand? Your vision sensors are fired where you can see and decode this is a mobile phone. And the text that I'm telling you with my mouth, like it's a 20 megapixel camera and it's a 40 GB RAM and etc. etc. So your brain is actually processing 2 inputs simultaneously, the vision input as well as the text that I'm telling you. So currently, Flava, this is OpenAI, this is Clip model. So for pharmacy people, you should think, maybe Rakesh Joshi will come in the second half. I'll recommend all of you to attend his lecture because his lecture is very much focused on my lecture is generic, but Rakesh Joshi will come in the evening and he will tell you some use cases. Now, the same use case. Now, my task that I'm trying to give you is that as a pharmacy people, tell me, you formulate a problem with this model where you can look into a picture, okay? And there will be some information, some pharmacy information given, and then you process it. For example, you are a pharmacist, you will look into something, a photograph, I don't know, some slides, something. And with that slide, some information will be given, some value, some biomarker, something. So as a pharmacist, your vision sensor and your vision sensor, which you have actually seen the image and some values, some biomarkers, I don't know, some texts, some DNA sequence, something you have. So when you look into both this, you make decisions. So it is not a single mode thing. So you see, what I'm trying to tell you here is that this is OpenAI's Clip model. If you can formulate a problem on the basis of this kind of models, you are 100% sure for Q1 rank top-notch journals. Are you able to understand? I'm showing you a dog and I'm telling that some information about the dog. and the machine is reading the text as well. Now you see the point is how the convolution is happening, how this this tokenization of the vision encoder and the text encoder is happening. This is what it's showing. So you as a pharmacy scientist start thinking of a problem where you can use AI, for which you need a vision. You look into that. See, you look into an image, you read the report, and you make decisions. AI can do this for you using this model. This is a very latest model. Of course, there is a more advanced weights for this called as MedClip. This is the same model for Flava. Flava is given by Meta. You know the Meta company? Meta is also a very big company. They also have a lot of money. So Flava. So I'll definitely look forward to, maybe Chisme sir and Tanvir Nave sir, aap log usko dekhiyega. These are the problems where students can formulate problems. And I'm looking forward to next semester when it comes up. 2-3 बच्चा आप लोगों का कोई MTech बच्चा, I mean, I don't know, whatever degree you give, your BTech, I mean, B Pharma, somebody should formulate problem. Maybe you are the supervisor, or you take one supervisor from the AI and formulate something like that. Let's say there is a pharmacy related image and the text, train it into a model, and the pharmacist who gives a decision looking into the image and the text, that can be trained this. So this is what I'm looking, and this is why, importantly, this session, this is Flava. Flava is also open source. The good thing is these are open source models. Okay. From your side, what I expect is formulation of the problem. Okay. And from our side, what you can expect is we will train the models. Maybe I'm coming to the last part of the thing. This is agentic AI. Now, what is this agentic AI? Anyone of you have heard about agentic AI agents? Anyone? These are the super latest things happening. This is crazy, actually. Now, what is this AI? Now, till now, AI was a task solver. Okay, so if I ask you a classification task or a regression task or an object data, AI was doing some generation tasks, etc., etc. Now, agentic AI is a sequence of agents. There are multiple neural nets which are connected in such a way there is no need of human intervention, and the task will be solved. So, make example. It will be easy for you to understand. For example, I am asking my model a question. I have $50,000. Tell me, should I invest in NVIDIA company or should I invest in Tesla company so that I get good returns of 20% return after 1 year? So this is my question. My question is simple. I have $50,000. I want to invest for 1 year or maybe some 6 months or 1 year, and I want 10% return, 20% return. And tell me, should I go for Tesla company or should I go for NVIDIA company? This is the question. Now, how many tasks are involved? Now, the agentic AI, if there are now there are fintech also agentic AIs are coming up. Now there will be several neural nets. Every agent is a trained neural net to solve a particular task, and they are all interconnected in such a way that the output of one becomes the input to the next, and the entire process is happening. Now, to answer this question, where should I invest, Tesla or NVIDIA? Now, what will happen? There will be one neural net. I call it as an agent, the first agent. It will go to the Yahoo FinTech or somewhere. There are a lot of websites where it will see like last 1 year how NVIDIA has performed, last 1 year how Tesla has performed. It will try to derive out all the the time series analysis, and it will try to understand, like, let's say last 6 months, last 3 months, last 1 month, what is the trend which is doing better. Try to make some comparative analysis for this one neural net is trend. So I call it as agent 1. First agent is doing this task. Now there will be a second agent. Now the second agent, what it will do is that it will go to all the social media, it will go to all the newspapers, it will go to all available resources to understand what is the sentiment of NVIDIA and Tesla at the current moment. Whether there is, there are sentiments. Like the CEO is he has given a news that Tesla is going to invest so much money in this. And in social media, there will be some critical, there will be some neutral, there will be some positive feedback, there will be some negative feedback, and there will be some neutral feedback. So the second agent is trained to go across the media and understand what is the current sentiment of these two companies and if you see the entire process, there will be agent 3, agent 4, agent 5, and the inputs of all these things will be going to another agent who is going to weigh them together to give you some kind of a thing, and the entire loop is closed. Now, let us say my task is whether I should invest in Tesla or NVIDIA. So I will, let us say you are my teammate. I'll say you do the regression of the last 5 years of this time series. Maybe you are my teammate. I'll say you do the sentiment analysis of this. The third person, I'll look into the senior management. Who are the people there? What are their visions? In which area they're investing? So now the fourth person, I will tell something. So 5 tasks given, and all these 5 tasks when returned, once again will be computed to understand which has a better possibility of that. Now, if you do it manually, there is human intervention involved at every step. And agentic AI will do it completely as one go without any human interventions. Okay, so I think, I think time is also up. This is our center. This is at E3 block. You can note down E3 block, room number, E3 block, ground floor, room number 16, E3G16. All of you are welcome to plan anything, work on anything. However crude is your idea, however raw is your idea, you're always welcome. There are a lot of innovations going on, so most likely this is beyond my scope. So maybe quickly, couple of them I'll show you. This was, I think you can see, the white shirt is me actually. The white shirt is me next to our Honorable Chief Minister. This was 26th May 2020, COVID times, you remember? And the next to Chief Minister, the purple shirt is Rakesh Joshi, who will come in the evening. The next guy on the other side of our Chief Minister is Rakesh Joshi, who will come. So interesting, you see, you remember this is 26th May. The entire world was suffering for all this problem. There was no RT-PCR kit that time. So we trained deep learning models, and in some hospitals of this one, take a chest X-ray, one single click, we will tell you whether it is healthy, whether it is viral pneumonia, whether it is bacterial pneumonia. The papers are published. You can read more about it. If I have something interesting, I'll show you. This is also interesting. This is a work which we did. These are some use cases. This is a cardiac monitoring system. This we did with SGPGI, King George Medical University, Lucknow, Vasant Kuj Hospital, Delhi, then a few more hospital associated. So we have made a small device. Take the PCG, the phonocardiogram, one single click. It will tell you whether your heart sound appears to be normal, or else we have trained it for 4 diseases: aortic stenosis, mitral regurgitation, mitral stenosis, and mitral valve prolapse. These are the common diseases. If you're interested, you can come to our lab. We'll show you many papers. More than 30 research papers are published on this. So you can formulate this problem. Now, this is a machine learning problem of, now what is this, in our country, you can imagine the cervical cancer load is very high. Now, pap smear and all are very costly business. So here, a small machine learning model we have trained. We have taken data from King George Medical University. So what we have done is that the apps are ready. Anyone interested? In the evening, I think in the second half, some of you will be coming to this lab. We will show you the apps, the working model. You can try for yourself. So what you do, any female, have to punch in these data, risk factors like age, place of, these are some demographic, and you have to do it blood test. I think 150 or 200 rupees blood test you have to do, and some parameters. I think you can recognize the parameters. These parameters you punch in our machine learning model, it will tell you how close the person is towards cervical cancer. Now, breast cancer, similar story with breast cancer. So you can see here in breast cancer also, once again, breast cancer is mammography, very costly business, right? So here the same story, some demographics, and with a blood test, you need this beta, HCG, AFP, PD-L1. So these are the parameters in which you have trained the model. Enter these models and single click, we'll tell you whether it's healthy, whether it's grade 1, grade 2, grade 3, or grade 4. So these papers, you can see the papers are published. I'm leaving this PPT in this desktop. So, sir, आप दे दीजिएगा किसी को भी चाहिए. You can take the PPT, and if you want to read more, you can always reach me. There are many work. I think this is interesting. This is an ongoing research work. This is an ongoing research work. ये मेरा एक funded project है in collaboration with NI people. Now, this is very interesting. I want the pharmacy people to listen to this. What we are doing here is that, there is a network called as this one, your Virus Research Diagnostic Laboratory Network, VRLD. This is an ICMR thing. Okay. I have access to 40 lakh patient database. Now, what we are trying to do here is that based on the symptoms, we have made an app. In the evening, we'll show you, in the afternoon, we'll show the app also. We have made an app where if you punch in this data, so this is, you see the data has been collected across the country, 40 lakh patient database we have. So I'll show you that this is how the app will look like. There are some symptoms. There are some symptoms. Can you see some symptoms, some respiratory system, some fever symptoms, some diarrhea, and you have to click, you have to check out which are the symptoms. And then with the confidence score, it will tell you what is the probable virus, whether it's a dengue, whether it's a chikungunya, what is that like? So that proper pathological tests can be recommended. Are you able to understand? Normally doctors get confused. वो 4 tests लिख देगा आपके लिए. बोले dengue भी कर लो, ये भी कर लो, 4 tests you will write. So this will be inaugurated next year by the health minister because we are doing with the DHR, the department of. Now these are the things we can do. So pharmacy people. Anyway, I'll stop this is a long PPT. So I will tell you, thank you so much for your time and interest. So we have got many problems. We have got many research problems where we can connect, and I will say thank you for your time, and the opportunities that galore at us to use AI in pharmacy is infinite. make it up and try to find some kind of problems, and we're always there to collaborate. Thank you so much for listening to me. If you have any question, you can ask me. Otherwise, yeah.
Thank you so much, sir, for setting this stage with such a comprehensive and interesting perspective on artificial intelligence. It is now time to hear from our keynote speaker, Dr. Shiv Prakash Ratnam, sir, CEO, Apicul Pharmachem LLP, Ahmedabad, and President of the Indian Pharmacological Society, a highly accomplished professional with a PhD in pharmaceutical sciences. Yes, sir. And over 30 years of experience in the pharmaceutical industry. He served at Jadis and Sun Pharma in various capacities in the area of pharmacology and drug discovery from 1991 to 1998. Started his own company, Synchron Research Services Private Limited, a CRO, in 1998. Synchron is the first CRO in India in private sector. At present, he is the founder and managing director of Synchron Research. Started Intervene, a research lab for clinical trials in 2006. He is the founder chairman of the company. Started Advanced Pharmacotherapies in 2007 for alternative therapies for neglected disease. This company innovated natural products for those diseases for which there are no allopathic interventions in the area of wellness, beauty, and longevity. Started Novelgenics in 2011, a niche generic company for regulated markets, filed several ANDAs and in USA and marketing authorization in UK. He was the former chief editor in Indian Journal of Pharmacology and also former vice president of Indian Pharmacological Society. He has more than 100 research papers published in various international and national journals, written many articles in various magazines and book chapters, and co-authored a book on screening methods in pharmacology. He has awarded with Udyog Ratna Award by Institute of Economic Studies in 2008 for his contribution for the development of clinical research in India. Awarded Distinguished Alumni of Government College of Pharmacy. He was recently recognized with the Amity Entrepreneur Excellence Award for his visionary work. Currently, he serves as a President, Indian Pharmacological Society. Let's give a warm welcome to our keynote speaker, Dr. Shiv Prakash Ratnam, sir. We welcome you, sir.
Thank you so much. I hope you hear me.
Yes, sir.
Thank you so much for the kind introduction. Good morning to all of you. And it was wonderful to be here today morning, uh, addressing you people in such an important gathering for knowing about artificial intelligence in drug discovery. First of all, my thanks are to Professor Chitme, uh, Professor Tanvir, and Professor Datta, and Vice Chancellor ma'am, and many other faculty members of Amity University, and also the participants and the speakers for today's conference. It was a mesmerizing talk by Professor Datta. It's an education for me to understand the importance of artificial intelligence and its use in various problem solving areas, especially in healthcare. And I must tell you that there were a lot of revolutionary aspects happened in pharmacy, starting from introduction of computers and programming for pharmacokinetics. If I remember in early 90s when I was doing my PhD, there were no softwares for solving even simple pharmacokinetic parameters. So I myself had to write an 800 line program to solve pharmacokinetic problems, because they're all mathematical problems, and there were no softwares at the time. So I had to write myself to complete my PhD, and that was an amazing opportunity, to write models solve them, and then optimize, writing optimization programs to solve such complicated problems. But the revolution was uh, to solve the iteration, because of the human intervention in iteration of for optimization problems are humanly impossible. So we needed computers to do that in early 90s. But today, after listening to Professor Datta, I'm sure that the time has arrived to really revolutionize the drug discovery program. So if drug discovery programs traditionally takes about 15 years to find a drug, millions of dollars, you can, these are all always, in every conference we talk about that. And most of the, drug discovery happen maybe due to serendipity, or maybe due to conventional methods of, um, knowing the structures from natural sources. But they were all not sure, of, eventually finding a drug. That is the reason why it was taking a lot of time, a lot of money, and also, a lot of resources. It's manual intensive at the time, and there were no computers, and people have to make intuitional judgments to discover a drug. But today we have a definite tools, to make such decisions using less money, using less time, and using capabilities, which can be revolutionary. I myself trying to build a company based on AIML for drug discovery. So I'm finding it so fascinating that we wouldn't have done that just even before 3 to 4 years back. If you see, the revolution happened in AI, and especially generative AI, which Professor Datta just showed. He may have not spoken about how about drug discovery and all those things, but his introductory talk gives you a fundamental direction to pharmacy students and scientists and medicinal chemists. How can we use such fundamentals of artificial intelligence and do drug discovery? How we can use databases, and how we can use chromophores, and use iterations, and generative AI, and eventually derive a drug, and also do some in vitro analysis of other efficacy. And also, I agree with Professor Datta that the Chinese people's invention has really disrupted the AI markets. And if you look at if you look at the overall international scenario of using artificial intelligence in drug discovery, my own research, while I was doing some research about what is this market size, and where are we per se compared to any other countries, including our own real closest neighbors, China. So we are not even very close. We are not even scratched the surface of AI in drug discovery. We hardly have any company in India which is even trying to do drug discovery using AI. So that's very pathetic of us, with so much of intelligence in computer sciences, and we are one of the largest hubs of IT, and we are not able to even come out with a company which does AI in drug discovery programs. Even most of the pharmaceutical companies, which are such large pharmaceutical companies, are not even investing in AI programs for drug discovery because of their very generic nature of making money. And if you see the maximum amount of licenses in biotech happening from China, startups from China, and about 150 to 200 companies are using AI for drug discovery, and raising billions of dollars. And where are we? That is the question, which we need to ask today in this conference. Somebody is going to, deal with this in the entire day. That I feel really sad about about not investing appropriately uh, on AI for drug discovery programs. So here is an opportunity for all of us to use AI for drug discovery programs, and most of the world leaders have very positively come out in favor of AI using drug discovery programs because it is going to save billions of dollars in making drugs. Not only small molecules, because the availability of druggable targets are so high now that AI is going to help us to discover drugs for those ailments which are neglected, or thousands of diseases which do not have drugs. We can have drugs for such diseases, and we can use less money, less time to discover such drugs for such diseases. This is one of the thing I would like to do, and I was in touch with Professor Datta and many other such experts to see whether I we can put a team of experts in creating a company which does AI for drug discovery programs. Since from 1 year, I've been doing research on how AI is playing a very vital role in drug discovery programs. And I find, India is in the best position to use AI because we have huge databases of natural products. India is in the forefront of using natural products. Even today, our country uses the largest amount of natural products to treat diseases. And every natural products have got a chemistry, and every if you take any plant, any extract, you find chemistry there. So we haven't exploited such chemistries to find drugs for various therapeutic areas. uh, Maybe in the world 1% of the 65% of the drugs which are discovered in the world come from natural products, and only 1% of those natural products have exploited. There is another 99% of natural products and chemistry need to be exploited. It's out there, in the outside of the realm of the human intervention. So this AI gives us an opportunity to exploit those 99% of the natural chemistries to do more discoveries for products. And India is poised to be in the best position to do that because we are the proponents of Ayurveda, wherein which since from thousands of years we have been treating a lot of many diseases using natural products. So natural chemistry is one thing which I really propose for Indian students in future, our companies and the universities to exploit them for drug discovery programs. And there is a convergence of such expertise. I must congratulate MET University to having a faculty like Professor Datta and the department and their investments in creating AI faculty, and the availability of the talented faculty members to teach students about the fundamentals of AI, which is very much essential. Because 3 years back we wouldn't have done drug discovery in such a fast pace uh, compared to today. How we are talking about how fast we can do drug discovery. But given that it's not easy to do a drug discovery, including even using AI, it needs a lot of talent. It needs a lot of interdisciplinary collaborations, like like chemists and medicinal chemists, chemistry people, uh, people who synthesize compounds, and people like the computer engineers and talent from AI. It is a new paradigm shift, and we are now seeking a new collaboration and new opportunity using AI and the pharmaceutical sciences are going to be will change forever, and this is unstoppable, and it will not stop here. It's an explanation. It is an explosion, like Professor Datta has put, like, before that it was static, it was a straight line, and suddenly in 3 years you saw that it is just an exponential growth of AI, with so many tools and open source tools available for scientists like us, to do drug discovery. I'll not take much time, because I'm not an expert on AI, but I'm an entrepreneur which would seek AI intervention into drug discovery. I'm the one, who can facilitate using AI and medicinal chemistry and our databases, to create a company which can be a drug discovery company, first of its kind, using AI ML. That's my job. That's where I come in, because at entrepreneur level, an entrepreneur, who can only facilitate, because he has got no expertise. So only I can do is bring people together, create a company, raise money, and see that we can do something different. And unfortunately, we haven't done anything yet. And Professor Datta and I was talking some time back, and he says that we haven't done anything. Let's do something. And maybe I will get an opportunity to work with MIT University in collaboration, to use the capability of MIT University's AI facility, and maybe see in another 5 6 years we come out with a drug for some rare disease, and that should be first step in revolutionizing and using AI for drug discovery programs in our country. And I thank you very much, MIT University, for inviting me as a keynote speaker. I can only do so much. I'm sure we have such amazing experts. I'm seeing their topics of discussion, and that would give you more insight into the very scientific aspects of AI and its use in drug discovery programs. And even I would look forward working with those speakers too in future in my life, if at all we Epicule comes out with an appropriate funding to collaborate with such brilliant minds who are there in this area, so that we all put our heads together and create something which India also gives to the world, one of the drugs to treat some of the rare diseases. Thank you so much, and I wish you the best for this conference's success. Thank you so much.
Thank you so much, sir. We are grateful for your time and support. Thank you so much for your visionary words and for sharing your expertise with us. Thank you. We now begin with our first scientific session. We have our first distinguished speaker with us, Professor Ravi Shankar Ramachandran, sir, Chairperson and Chief Scientist of the Biochemistry and Structural Biology Division at CSIR, Central Drug Research Institute, Lucknow. He earned his PhD in molecular biophysics, structural biology from Indian Institute of Science, Bangalore, and postdoctoral research as an Alexander von Humboldt Fellow under Nobel laureate Professor Robert Haber at Max Planck Institute of Biochemistry, Germany. With over 25 years of research experience, Sir specializes in structural biology, nucleotide repair, and drug discovery, focusing on Mycobacterium tuberculosis. His groundbreaking work includes the discovery of Mycobacterium barosomes, novel messenger RNA repair mechanisms via ribosomal protein RPS3, and first-in-class inhibitors targeting DNA repair and feast-famine regulatory proteins. He has authored over 95 publications, hold multiple patents, and has supervised 22 PhD students. Professor Ramachandran has led translational efforts, including phase 3 clinical trial for Unifanovir against COVID-19 and technology transfer for antiviral therapies. His contributions have earned him prestigious awards such as Tata Innovation Fellowship 2022, Nobel Bioscience Award, and NASI Scopus Young Scientist Award 2010. He serves on key national and international committees, including the Task Force on Repurposing Drugs for COVID-19 and the Research Advisory Committee at King George Medical University. I welcome you, sir, to deliver your talk on AI approaches in rational drug discovery. Welcome, sir.
Yeah. Hello, can you hear me?
Yes, sir.
Oh, wonderful. A very good morning to all of you. It's a great pleasure to be here. And I think it's very important. We are on the cusp of great transformation. Although AI has been used in drug discovery, say for the past more than 10 years in all seriousness, but now we are on the cusp of a real transformation. And once again, I welcome you all. I am saying a big hi. I can see my friend Dattaji sitting there. And I think that must be Dr. Chitme beside him. Yeah. Hello, sir. Hello. And the Vice Chancellor and other people. Yeah, it's a great pleasure. I would have loved to come personally, but we all are always occupied. And this is the age of electronic and modern communication. So big hello. Without further ado, I'll share my presentation. Just a second. Can you see my screen?
Yes, sir.
Ah, great. Wonderful. Okay. I am Ravi Shankar from CDRA, and I met Professor Datta during his time in AKTU. And correctly, as he said, during that COVID-19 period was a big coming together of many scientists. And I was very impressed by the AI work going on in his laboratory at that time in AKTU. One of the things which impressed me at that point of time, and he didn't show you in his presentation earlier, is that just with 10 seconds of video on your mobile phone, you can kind of sort through 39 or 40 odd mental issues. Like, are you totally stressed? Are you having any difficulties, etc.? So this is at that sphere, and I was very impressed at that time to see this happening in his laboratory in AKTU, and subsequently the newer apps are also very exciting. So I congratulate Amity again for setting up this wonderful AI department there, and it seems to be doing very well. As we know, science is transforming global health and saving lives. In the past 100 years, human lifespan has increased by 23 years, and we are generating, as scientists, treatments and cures for some of the most devastating diseases. And in the recent past, 82 new vaccines and diagnostics, drugs, etc., have been introduced since 2000. The new meningitis A vaccine has already saved almost 4 lakh lives and prevented nearly 7 lakh new infections. Malaria drugs have helped reduce childhood malaria deaths by 65% since 2000. And the newer next generation drugs promise to do even more. But having said that, and as many members of this audience will know, drug discovery is a challenging task. For example, in antibiotic discovery, even after you discover a new antibiotic, non-adherence and the bacteria's own ability to mutate can lead to the new antibiotic not being that effective within a few years. So we have to always keep a step ahead of what nature and the pathogen throws at us. And AI is transforming this space by speeding up processes and reducing costs. Because each time you have to do something new, you have to invest a lot of money. And at the same time, take an example just of this antibiotic resistance. You have to come back and again go to the drawing board for a new approach to kill the pathogen. So by speeding up processes and reducing costs, we can hopefully stay one step or two steps ahead of resistance. It's unavoidable, but we can keep ahead. And like Professor Ratnam, who came before me, he was saying that the average time required to find a new drug in the conventional scheme of things is about 15 years, 10 to 15 years. And the failure rate is about 90%. So only 10% of molecules which you think will succeed through clinical trials and enter the market actually get through this phase. And it costs about $2.5 billion on an average to get new drugs into the market. But with AI influences right now, it costs about 1 billion USD, and the success rate has increased by 2.5 times to 25%, which is huge because the most money is spent in the clinical trials and the developmental period in the later part of the drug discovery chain. I'm showing you the slide to show that in very recent times, a plethora of companies have come. But unfortunately, none of them are in India. Like Ratnamji also said before me, there is a huge need for companies, AI companies, which can be built up ground level onwards in our own country, because we don't lack in quality manpower and we don't lack in this thing. It's just kind of bring everybody together. I think we should be there. So this is in the preclinical space of drug development, and there are logarithmically more companies in the even the earlier discovery development, right from 2012, 2013 onwards. The promise of AI is that it will help us accelerate discovery in all stages of the drug development process. And it promises to be the backbone of rapid and more effective discovery of therapeutics. When I say AI, I am taking recourse to this definition that it is any technique that enables computers to mimic human intelligence using logic, if-then rules, decision trees, and ML, including DL, right? So let's say this is the relationship between ML, AI, and DL in drug development. There are different kinds of AI, if I may so say. This was highlighted by Professor Datta in his introductory talk. You have machine learning based approaches for target identification. And this enables us to analyze huge amounts of omics data, genomics, proteomics for drug targets, and to predict protein drug interactions with, say, these other algorithms like random forests or deep neural networks. We have deep learning for molecular design, generative models. There was an example shown for image generation by Professor Datta earlier. Here, if I take you to an analogous example, you have a starting inhibitor, and you want to make variants of this inhibitor to help it to overcome any bad properties, improve affinity for the target, and lose toxicity and other unwanted properties. So you generate a good starting set of molecules based on GANs, generative adversarial networks, etc., novel molecules, and then you evaluate them against the targets. Often the structure of a target is not there. And here again, recent advances by, for example, DeepMind AlphaFold, and this helps get a initial structure of a protein for almost for all the encoded genes. And then you can then analyze possible interaction of these predicted molecules for rapid identification of inhibitors with better properties and therapeutic potential. Reinforcement learning for optimization of these compounds is then done. And here this includes predicting the ADMET properties, absorption, distribution, metabolism, excretion, toxicity, etc. And these are important because often you need to have a therapeutic molecule in your body for as much time as needed. It should not be present in your body infinitely. It should also go through a process of excretion. It should also not have any toxic effects. It should preferably accumulate in the organs of interest where it's needed, and it should be available in sufficient quantities without eliciting toxicity, such that it can target, for example, if it's a bacterial thing, it should have enough minimum inhibition coefficient for killing the bacteria. So availability, bioavailability. So these are all done. And then we also use natural language processing methods, knowledge graphs, to mine literature and patents for drug target relationships, which may not often be easily imaginable or easily be correlatable. And this is something AI is very good at. And this can include extracting insights from the PubMed or clinical trial databases, etc. Literally, we are starving for knowledge while drowning in a sea of data. I alluded to AlphaFold prediction of 3D structures of proteins. And here, it has been found that in the vast majority of cases, the predicted structure of AlphaFold is quite close to the experimentally determined structures. Of course, not in all cases, but it gives us a good starting point to start experiments, and in the absence of any other information, to take things ahead based on this information. So this is an important supporting thing for us experimentalists. Reinforcement learning, I mentioned in the overview slide, for optimizing molecule properties. This can include the charge complementarity, shape complementarity, score it better, get back. Then in the next stage, at each stage of drug discovery process, you may want to eliminate unwanted properties, add on better properties. Maybe you're not able to get good formulation, so you need to change something. You need to make a better salt, etc. So this goes in an iterative manner till you get the molecule of desired properties with desired amount of affinity to the target. And to find unanticipated linkages between a target of interest and a molecule, for example, there are approaches like word cloud and network graph of literature mining results, and these can find unanticipated linkages. See, as a human being, obviously, we cannot think how much ever you read. It's difficult to keep all the information in the head and then try to find linkage. Oh, I read that here, I read this here. AI does this best. It finds out all those unanticipated linkages, and I'll show you a couple of case studies where it works wonderfully well in extraneous circumstances. One such example is that of amyotrophic lateral sclerosis, a motor neuron disease, where the patient's muscle control, everything systematically goes down over time, and it will lead to, it's irreversible, leads to death. There was no treatment available. My own PhD supervisor, Professor Vijayan, he died of this. And it's really suffering to watch, both for the patient and as for the loved ones. Benevolent AI is a company, AI-based company. It pioneered ALS drug discovery and AI-driven drug candidates, BEN 34712 and 9160. These are in clinical trials right now. And the methodology used by them, they employed initially a knowledge graph that integrated over 85 diverse biomedical databases, and they processed more than 35 million scientific papers using natural language processing. So to identify the linkages between the disease progression and possible targets. This knowledge graph approach identified relationships between genes, protein, disease mechanisms by analyzing various probabilities in literature, and enabled hypothesis generation for a new target identification itself. It showed and identified two novel targets which were never anticipated earlier. One is the CABL enzyme as a novel target for ALS treatment, and the other, the RAR alpha beta, retinoic acid receptor alpha beta, which I'm showing you the structure on the right hand side. And against each of these targets, it led to the development of two molecules which are in clinical trial, the 9160 and 34712 molecules. And this approach allowed rapid scanning of vast data sets, hidden connections, You got the targets of interest, which was never known before. It was an untractable problem, and it reduced the time needed for target discovery to beautiful new compounds. So this novel target prediction is something where it excels for diseases which have not yet been tractable, where you still don't have medicines, and where we still don't have that much of knowledge in terms of how to target the disease from this vast amount of data. And this is something which AI did well. And AI techniques like machine learning and deep learning are key in target identification drug design. Here, structural biology approaches would decode molecular architecture. And I told you about AlphaFold also, where in the absence of such information, you can still glean it from approaches. And we have this huge data for discovery, and which oftentimes we can't make sense of. And AI approaches will actually link these vast data sets. The other example I'll give you, a case study, is that of this company called In Silico Medicine. And their molecule went to clinical trials, phase 1, in less than 18 months. What is the original one? 15 years, 10 to 15 years. Here you have something which has come through in 18 months, target identification to phase 1 clinical trial. Amazing, right? So here, what did they do? They use a target discovery tool. Each of these companies have their own proprietary tools, but essentially using this approaches which I enunciated earlier. And they identified a new target for idiopathic pulmonary fibrosis. What is this disease? Systematically, the lung tissues keep hardening. There's no cure, and the patient will ultimately die. And here they identified TNIK, a kinase, as a novel therapeutic target for idiopathic pulmonary fibrosis. They integrated multi-omics data sets from patient tissues, so experimental data, clinical data, annotated by age, sex, natural language processing. They analyzed millions of data points from patients, research publication, grants, clinical trial databases. As a scientist, almost impossible to get these linkages in my head, right? This could do it. And identified this target, and they have another platform. Literally, for example, target identification characterization literally takes years, right? They could do it in months. And then they have a platform called Chemistry 42. It is again based on generative AI approaches like GANs, etc. Right? And that could design novel small molecules. They design just 70 to 80 molecules. Normally, in a program, an inhibitor identification program, you would literally evaluate lakhs of molecules. Here, you predict molecules, you evaluate them in silico itself for various positive properties. You used reinforcement learning, transformer-based models, and identify drug molecules with optimized properties. 70, 80 molecules, maybe a lot of luck also. And they tested the lead candidate for 055 was optimized for the ADMET properties, which I told you, which is needed earlier for drug discovery in the later stages. And they did find molecule with minimal toxicity while retaining high TNIK, the target affinity. And right now, it went through the phase 1, phase 2, and as of 2024, it entered phase 3 and showing good significant promise. And in both USA and China, this is the phase 2 trial which they conducted between 2023 and 24 with more than 71 IPF patients. And the cost, the preclinical development cost 2.6 million compared to about 400 million. Why? Time saving, cost saving. You saved a lot of money in synthesis, and as well as in the design of clinical trials. AI is again playing a very important role in design of clinical trials. Possibly it is able to also do good documentation, which is needed for regulatory approval. And the timeline from target discovery to preclinical candidate nomination took 18 months, with phase 1 trials initiated 9 months later. This is amazing, believe you me. And this example underscores the role of AI in rational drug discovery. It accelerated target identification. I showed you 2 cases, right? Both with Panda Omics and with that benevolent AI in motor neuron disease. And optimizing molecular design reduces costs and time, and clinical validation, right? In all these things, it plays a very important role. Now, drug repurposing. The same company, Benevolent AI, when COVID struck us, they had the tools ready, right? And this was a typical moment for them to test out their tools for COVID. Once they knew the symptomatology of COVID and that it is a virus, it's similar to coronaviruses, and that it also leads to inflammation and the cytokine storm, which was a major thing in the first wave and the second waves. They analyzed that they use the same approach, but that's 85 scientific databases, 35 million papers, etc. They plugged the thing into it. They found a molecule called baricitinib. This is from a database of already approved, FDA approved drugs. There are about 3,000, 3,200 drugs which have already been approved. And they use this database. So it acts against a target called a kinase target called JAK1/2, 1 and 2, for rheumatoid arthritis. So it's a medicine used for arthritis. And they found that it actually can be repurposed to a target called the AP2 associated protein kinase 1, which is very important for COVID-19 as in the host, the human host. So it's a host-directed medicine, and also has some antiviral activity, direct antiviral activity too. And the process from this hypothesis to emergency user approval took 9 months, and full FDA approval in 27 months for COVID, compared to years for traditional drug development. So AI, the role of AI in target structure determination analysis, we saw in protein folding, structure prediction, AlphaFold, and more recently in cryo-EM advances and the integration of multi-omics data, this vast amount of data which we have in, say, proteomics, genomics, this one, lot of data, patient samples, experimental data. And in the last part of his talk, Professor Datta mentioned about this almost automated or autonomous AI, I forgot the exact name, but which links various networks together, right? So it's like autonomous. You have a problem here, it takes the results, put into the next set of neural networks, and so on and so forth. So this integration is an emerging trend, where we literally hope that if you given a disease, I plug something, maybe the system can predict targets, find molecules, and maybe with small experimental intervention can quickly lead to even candidate molecules for evaluation, right? So it is enabling breakthrough applications. We can dream about more developments in precision medicine. As you know, even population to population, and sometimes even between human beings, the efficacy of medicine changes, right? Small differences in the way we are, and the way the target, maybe there's some mutation in the target which is peculiar to our genomic strain or something like that. And personalized medicine, synthetic biology, and climate solutions. As the costs are coming down, now the cost of sequencing the human genome has come down to a few dollars, and that can now form the basis of the next stage again in breakthrough applications. But there are lots of challenges ahead. Data overload, ethical dilemmas are there. How safe is AI is a question often posed by various agencies, and we need to work in that direction to establish boundaries, ethical boundaries for AI. And AI is not some black box. It requires collaborations with various institutions, with expertise, where you apply artificial intelligence approaches. It is not a standby thing. It is something which enhances our own experimental and scientific queries. Amazingly, it's a very good helper. So let's imagine a future where we just don't decode life's secret, but we can redesign them for the good of humanity. And that's the promise of AI in drug discovery. The future is yours. It's ours. With the students here, there are vast opportunities in AI drug design, especially in our country too. We will have the first mover opportunity in whatever you do. and the ecosystem is now improving. We can move towards 3D printed medicines, where you have combination medicines with very precise roles. These are all very latest and upcoming things. Cures for the uncured diseases, I gave you a glimpse of that. Prediction, detection, ability to track emerging health risks, where normally you can't make out various factors and the way to put them together. And actually, we may be on a way to, say, pandemic, which is not yet identified, and this would help us identify innovation in formulations and all this at our fingertips. For future challenges, we need continued research investment. The regulatory landscape has to change to accommodate these modern approaches like AI. Recently, FDA has been approving AI-based diagnostics, right? So without non-invasive diagnostics based on AI for extreme challenges, we have our aging populations, chronic illnesses, mental health crisis. I give you a hint of based on what Professor Datta himself is doing there, and climate-related health risks. So there's a lot of excitement in drug discovery informatics. We have informatics and genetic diseases, diagnostics. The other excitement is that also now of this Neuralink, Elon Musk, right? The picture on the left shows you the size which is implanted in the brain, and lets even paralyzed persons communicate with their loved ones, and you can do stuff and even earn money. A paralyzed person can do now by communication, earn money also. So these are exciting times for drug discovery. The challenge in all this, like in every technology, is to make healthcare available to the common person in an affordable, equitable, and ethical manner. And effective use of AI with its ability to reduce costs has a critical role to play to achieve this. So I'll conclude with this, that the health challenges we face are vast, but so is the power of science and the optimism of AI in our hands, right? So thank you.
Thank you so much, sir, for your insightful lecture on AI approaches in drug discovery. I would like to request all the participants that you have the wonderful opportunity to interact with our esteemed speaker. If you have any questions, you may ask. I would like to request all the participants joined online. If you have any questions, you may ask. We will let you in, or you can type your question in the chat box also.
Yeah, sure.
Any questions? Any questions from the online
Yeah.
participants?
They are still digesting this new information, I'm sure.
Anyway, this is M.K. Datta. So thank you, Ravi Shankar sir, for so much interesting and enlightening talk. We remain grateful. Anyone has a question? Okay. So thank you, sir, for.
Yeah, sure.
Somebody has a question, I think. Yeah. Yeah, you can ask, please.
Hello, good morning, sir. Sir, my question is, like, for the treatment of tuberculosis, there is not even a single drug up till now.
No, man. No.
No, not even a single drug is
No,
used
no.
for
For
the
TB,
treatment
we have
of tuberculosis.
fantastic.
We
We have
have
the
to take
DOS therapy.
combination of drugs.
Yeah. Single drug we don't have, but the nature of the disease is such that a single drug, right now, the treatment regimens are very long. Our dream is to have shorter treatment regimens,
Yes.
and we are going towards that. For example, the new bedaquiline, and one more, the thing which has come with an early, the target is nucleotide synthesis, which just came out now in Nature or Science, Anil Kaul's paper. So that's the second molecule, wonderful molecule which has come up. So these all are going on, and I can anticipate a question: can AI do something here?
Yes.
Of course, we are all excited about it, but I don't see actual work going on in this area right now. And young people like you can carry this on your shoulder and visualize. Let's see what all we can do. We have super data around. We have a lot of information. It's an ancient disease. So can we put it all together to find out new therapeutic approaches which can shorten therapeutic durations.
The regimen has to be like.
Yeah.
Yeah.
Now,
Yeah.
literally, you take it for 3-4 months, 6 months. Multi-drug resistance is a huge problem at some, etc. But things are going on there. So these are the kind of things where we literally need new approaches, new things to shorten. Patient compliance is a big problem in TB, which has also contributed to drug resistance developing. You take medicines halfway through, you start feeling literally in the first 3 to 4 weeks, you start feeling very good. After you take medicine for TB, your symptoms kind of vanish, your fever goes away, coughing reduces, and patient think, "Arey, main to theek ho gaya hu," and they stop. But the bacteria knows the adversary, right? It's been under the pressure of the medicine, so it knows, and resistance then develops. This has been a contributing thing. It's multi-pronged approach. Yeah, and AI has got a good role.
Yeah, we can be able to develop some single molecule.
Sure. I'm optimistic. Not only for TB, for many of the other antibiotic resistances and similar kind of things also, it's very important. And diseases which are till now untractable. We don't know. So can we use approaches like I showed you the 2 examples to find new targets which we can't even find linkages between them. Right?
We have a question. Thank you so much, sir. We have a question in the chat box.
Yeah.
It's from Dr. Saurav Verma. Sir, is it you? To make the session more interactive, I think you can ask the question directly.
Thank you so much, sir, for giving a very nice lecture.
Echoing. Okay, how AI can assist in predicting admit properties. I read it in the chat box.
Yes, sir.
So I did give you the 2 examples there, right? Both for in silico medicine, they use generative AI approaches. First is once you find your initial inhibitor, hit molecule, and it goes through the preclinical study process like toxicity, ADMET, and all the stuff. You take those results, plug it back into the system. Because AI, when it had predicted, it reached the limit of its efficacy and efficiency, or the best molecule it could predict, it predicted in the start. Now, based on your experimental results, you feed it back to the AI, right? It'll again make a series of molecules around this. It says, okay, this thing is leading to toxicity. I will not disturb it. Let me change the other parts of the molecule while retaining the affinity of the molecule to the target, right? It has to retain a whole set of other good properties, Lipinski's rules and all that things like that, solubility and so on and so forth. While it is doing that, it does improve affinity and lose toxicity in a sense, its affinity to other unwanted targets. So this is a cyclical process as of now.
Okay, sir. Thank you, sir.
So, Dr. Ravi Shankar, sir, thank you so much for your, very simple and easy to understand lecture. It is a complex topic, and because it requires a lot of people to be involved into the project. I just wanted to understand, sir, is there can we use the AI in diagnosing the cystic fibrosis in the early age, like the genetic disorder? Since in general, this is genetic disorder, but
Yeah.
cystic fibrosis, so once the child is diagnosed, then their survivability goes up to 15 years. Then after that, it becomes too difficult to manage. So
I agree.
this kind of a disease can be predicted by using the AI.
Yeah. It is definitely possible with the right data and with the right awareness. See, often we just don't get access to diagnostic processes. Even with conventional diagnostics, not many people go or get diagnostics unless it's little later in the day. You see physical symptoms, earlier symptoms itself, if you can find out, and this is where AI can step in. Suppose with the ease in now sequencing our genome and series of questionnaires, I think it should be possible. It's a tractable thing. It should be worked on. If not already, it should be possible. And AI can definitely play a role.
As you know, the UK is already in the process of documenting all the DNA sequencing of every individual, and US has already done or majority of the population. But India being the having the
No,
large
no.
population,
Lot of efforts are there. Sequences across the diverse genetic population. We see we are not one. We are Hindustanis, but
yeah,
literally we have so much of genetic
diverse.
variations, right? We have a lot of different races merged in our system, and also with intermingling of various races, right? We are one Hindustan, and therefore a lot of effort is going on. We also have data which is kept. I think there are 3, 4 publications also available online. And I know for sure that it is an ongoing thing to maintain and augment our databases of our own genome. And it's not something, it's also has got implications in security of our country with bio warfare, etc. To find, suppose one set population is amenable to or can easily be affected, targeted with a certain disease. Now that's a biological warfare opening compared to others. So all these are now recognized very well. Literally, if you see a time point, I can see from around 2008, 2009 onwards in my, as I've been going to various meetings, I've seen this awareness coming up at the ministry and government level too.
We have a question from Dr. Borsalvi.
Good afternoon, sir. Thank you very much for your great insights, sir. We are one of the fortunate to get in, chance to get interact with you. Sir, after asking the question, getting the idea of DNA sequence in India, as a clinical pharmacist, I have my concern over the ethical concerns that are practiced right now in our country, as well. What are the challenges you feel as? And apart from the scientific innovation interventions and all, how dangerous or threat to the society of this particular DNA sequencing as a whole to the public, sir?
Ethics is very, very important. You see, that is why in the last 3 or 4 slides of my talk, I repeatedly stressed on ethical use of any, not only AI, any approach. See, an information about ourselves, our DNA sequence, or our disease profile, etc., can be wrongly used by various persons also. In terms of simple, the most basic thing is our access to health insurance and the cost of health insurance. Suppose the insurance company knows that you, a person based, they have access to our database of our genome, gene, etc. And they know that, oh, this guy is predisposed to heart attack, or this lady is predisposed to triple negative breast cancer, say. Then the insurance cost can go up. This is just one example. Then the other thing is in jobs. You may have your jobs also be affected by private companies which say, oh no, this person is predisposed to something. They may not be able to, maybe they are predisposed to depression, for example. Some of the depression is also predisposition comes through hereditary channels. And they may say, oh, this may not be a good match for a company, etc. So we have to protect the privacy of the common man's data, personal data, our own human body's data. At the same time, we need access also to all the therapeutic tools. We need access also to everything. So this is a delicate balance. We need effective regulation and we need the rules. That is why I repeatedly emphasize ethical regulation, and this is something we really need to work upon, not only here, around the world. It's an ongoing dialogue and a debate around the world in all countries.
Thanks a lot, sir.
Thank you so much, sir. It was such an interactive session. Thank you so much for joining us and sharing your knowledge with us. Thank you.
Bye. I'll take your leave. Huh?
Thank you, sir.
I have other things.
Moving forward for the next lecture, we have with us Dr. Feroz Khan. Sir is a senior principal scientist in the Technology Dissemination and Computational Biology Division at CSIR, Central Institute of Medicinal and Aromatic Plants, Lucknow. Dr. Khan specializes in bioinformatics, cheminformatics, and computational biology, with a strong focus on applying AI and machine learning technologies to biological and chemical data for drug discovery and development. He earned his PhD in bioinformatics from Dr. APJ Abdul Kalam Technical University, followed by postdoctoral fellowship at the SCAGGS School of Pharmacy and Pharmaceutical Sciences, University of California, San Diego, USA. Dr. Khan has developed multiple research tools and database, including AromaDB, QLED, DBMDR, and GRMAP-DB, and has guided over 12 PhD scholars and 70 plus postgraduate trainees. He has over 140 research publications and 100 plus invited talks to his credit. He is an executive member of Bioinformatics and Drug Discovery Society and a member of several scientific societies, including the Society of Biological Chemists and Society for Ethnopharmacology, Kolkata, India. I invite Sir to deliver a lecture on machine learning methods used in early drug discovery. We welcome you, sir.
Good morning, all of you. Thank you for the nice introduction. Are you able to hear my voice?
Yes, sir.
Thank you, organizing committee. Good morning to all of you for inviting me for this wonderful one-day national workshop on use of machine learning tools and artificial intelligence for effective new drug discovery and development. Organized by MIT Institute of Pharmacy in association with MIT Center for Artificial Intelligence, MIT University, Noida. As I just see that earlier in lecture, Dr. Ravi Shankar already explained most of the rational drug designing approaches which are nowadays used in drug development process, and a very genuine questions asked by the participant. And thank you, Dr. Datta, Dr. Chitme, and Dr. Ravi Shankar for wonderful organization of this workshop and giving the opportunity to express my view. So dear participant, I would like to share my PPT and then we will start with that. Participant, are you able to see the presentation slide?
Yes, sir, it's visible.
So the today's talk on machine learning method used in early drug discovery process. So in CSRC map, my job is to use the different AI and machine learning methods to help the wet lab scientist to validate the drug development process, even the herbal formulation process. And we are successfully developed few formulations or phytopharmaceuticals, even lead also for further clinical studies related to anti-malaria, anti-cancer, and psoriasis and anti-tubercular activity. So if you see the worldwide scenario, you will be surprised that in 2025, around 16 new drugs approved by US FDA. You see the list of the drugs I've shown here and the website where you can see more detail about these drugs. So you see the drugs approved in different areas belonging to either anti-cancer activity or antimicrobial activity and anti-diabetic activity. And you see vinceltinib and miratinib, basically they are the tyrosine kinase inhibitors, which are recently used in cancer treatment. So you see all these drugs uses somewhere in the process of drug development process, either machine learning method for screening of lead compound or simulation process. So two things are here. And for your research purpose, I would like to suggest you to concentrate on modeling, molecular modeling, and molecular simulation. Two different techniques are there, normally used in drug development process for early lead identification or early drug development. So you see the pipeline in the presentation, you see the normal pipeline mostly started with some experimental data in hand, and most of the research lab, they have preliminary data or what we call as training data, or in AI and machine learning, it is called as training data. So training data is none other than experimental data. You see, you should have at least some supervised data. This is also called as supervised machine learning data. So you should have some supervised data to train the model and develop the model with some authentic validation criteria. And after that, go for further model development process for virtual screening of lead molecules. You see, normally in drug discovery process, there are major four pillars where we use computational methods, mostly in lead identification, number one, lead optimization, number two, target identification, number three, and target validation, number four. These are the four major labs in most of the pharmaceutical companies and research lab integrated with chemistry, medicinal chemistry, as well as bioassay department, where in vitro or in vivo assay mostly done for the screening process or high throughput screening of active molecules. So animal scientist or where small animals are used, normally in CMAP we use small animals. CDRI is as small as well as large animal for testing. So before going for preclinical studies, these four steps I already showed here. We use computational approaches and then go for in vitro and in vivo testing on animal system or animal models, and then that is called as preliminary studies. And after got the preliminary confirmation for activity, we go for clinical research. The last step is clinical research, which is mostly done in hospital, government hospital, which are approved for clinical research testing process. We normally four phases of clinical research done. Number one, phase one, where normally normal patients, normal participant normally use for testing. And phase two, consider the patients which are affected with some disease, where on which the lead identified has been tested. And then go for, after confirmation of phase two, we normally approved the regulatory body of that particular country normally approve the drug to release the drug in the market. And phase three and phase four are regulatory observation period purpose phases, where normally regulatory body concerned about like side effect or toxic effect or lethal effect. And if there is any lethal effect, which is very toxic or risk assessment related things are reported by some users or patients or doctors, so normally regulatory body disapprove the drug and close the drug normally from the market. So this is a very soothing 5 to 10 years period or more, even 20 years earlier. Nowadays, using the computational method, it is 10 to 15 years normally takes the process to develop a single drug. And identification of Ayurvedic preparations or Unani preparations or herbal preparations or phytopharmaceutical, it takes less time because there is no clinical testing. Only the feedback of the patient has been taken, and normally that herbal supplement, they are approved as a supplement, not as a drug. They consider as a supplement and approved for market use. So that is the simple pipeline normally used in most of the research lab as well as in industry also. So you see in this diagram, I just covered the component of lead identification to target identification. So before preclinical studies, you can focus on these areas, and number of research lab where drug development process has been in is ongoing. You can, or even pharmaceutical companies, you can join in different categories. You see, I just show the pipeline of from where you can start with. Either you start with some medicinal chemistry group, or you start with some pharmacology person or the veterinary doctors or doctors group which are in vitro, in vivo testing lab. So you either focus on lead identification and lead optimization, and other criteria is those who have some knowledge of good knowledge of pharmaceuticals. As your pharmacy department, you should focus on identification of targets and their validation. So validation is again two types. One is theoretical, another is wet lab based. So you can select initially for theoretical validation and then go for wet lab validation. This way you can save the lot of wet lab economy and also the time for screening of potential molecule. So in lead identification, the normally the researcher use the method what we call as quantitative and qualitative structure activity relationship modeling. In short, it is called as QSAR. And other modeling approach is pharmacophore modeling, where we know the pharmacophore of the molecule, and medicinal chemists only want to do the analysis for a particular library, like indinone derivatives library or gallic acid derivative library, or other any terpenoid series or flavonoid series of the molecules. So natural compounds basically have very limited areas where you can focus for drug development process, because natural molecule easily metabolized by the cytochrome P54 enzyme family. So it is very tough to identify natural drug in very short time. So screening process takes a lot of time, and normally we come up with some fractions having a good activity. So focus on some activity and then identify these predicted leads can be identified for target validation. So we normally use the molecular simulation process for target binding affinity evaluation as well as target binding stability evaluation. So molecular modeling and AMD molecular dynamic simulation normally used for seeing the interaction of lead molecule with the potential targets. So target information are already there. You can discuss with your team member or your supervisor and select the appropriate target. Sometimes disease is concerned with single target, and in some time there are so many targets are involved regulating the disease. So multiple drugs can be used for the treatment of disease. So disease condition is not based on single drug. It may be depend on multiple targets. So normally what we call as poly-target analysis or polypharmacology, we use that criteria to target these kind of the diseases. So mostly in research lab, we focus on single molecule and then go for a single molecule having multiple target. For example, protein kinase inhibitors, they may target number of kinase family members. So a single drug can be used for multiple target, and that is called as polypharmacology. Okay, I hope you understand the point. And after identification of target, you can go for in vitro activity. It may be, for example, anti-cancer activity, or then go for ADME and PKPD analysis, and then go for animal testing, and then go for clinical research. So that is the pipeline normally used. So I'm not talking about the preclinical studies or clinical research, but major focus on to show the some of the highlights or areas where you can focus on your research work. Even you can do in university system also if you have a good lab, computational lab. It requires a lot of workstations, and for analysis you may use desktop also, but I suggest to use workstation or server. That is give you the much faster result. Now, let us start with the one method, what we call as QSAR. You see, the QSAR is basically a process by which biological activity of a compound is correlated with the physicochemical properties and expressed in the form of mathematical equation, what we call as QSAR equation. So here relationship can be made through either a statistical method as well as machine learning method. So there are so many methods I will show you later that which method you can use. So based on your expertise or learning, you can use any one or two method and try to develop the relationship model first. If you are able to develop the model with more than 60% or more than 50% criteria, then it is better to screen the molecules and identify the active molecules. So lead identification process and optimization required QSR model development. So this is a best way to express the relationship of chemical properties within the chemical molecule. And the question is why we do the QSR modeling? Because we know the compounds have similar structure, but activity is different. And in some way, if you see number of drugs, I will show you the example later that number of drugs are having different structures, but activity is similar. Even the similar structure have different activity. So why this is happening? We don't know actually. We don't know why the compound is active and why the why the compound is inactive or toxic in nature. So the reason behind the activity can be evaluated through QSR modeling. You can explain the mechanism of action of lead molecules by this method. If you see the new international guidelines, like US FDA already mentioned in their pro forma that, or even the website, you can go and see. They mention number of softwares you can use for developing the structure activity relationship. Earlier, they are manually done by the chemists, but nowadays bioinformatician or the computational biologists normally develop the QSR model and validate it first and then go for submission or approval process. So you see, SAR study is very common. Earlier, there is only the experimental SAR was there done by the chemist. Nowadays, it is a quantitative SAR. SAR means a structure activity relationship. So a number of example already mentioned in their website like Multicase, MDL Tool, TopCat, QSAR, DREC, Oncologist, and so many other software they mentioned for the pharmaceutical companies or the research lab to please first screen and develop the model through these softwares. And these software consider authentic, even the Discovery Studio, Schrödinger, and a lot more, Sibyl also. They are internationally checked software they are normally used in pharmaceutical companies for the screening of the lead molecules. Even the European group organization, what we call as Orchestra Group. Orchestra Group has given the guideline for developing a QSR model, what we call as REACH guideline. REACH requirement for QSR, they already mentioned in their website that before submitting for approval of drug, your molecule should follow these 4 criteria. So 4 criteria already mentioned in the list, and these 4 criteria basically indicates the process of model development, authentic model development, and you can like just hold. Are you able to see it?
Yes, sir, it's perfectly visible.
Okay. So these 4 criteria results are derived from QSR model, and this other is substance falls within the applicability domain of the QSR model, and the third is results are adequate for the purpose of classification and labeling, and the fourth is reliable documentation for QSR model. So you see the published paper, research paper for QSR, normally they explain these 4 criteria, which is normally required by the European group, which is working on a regulation of drug approval. And another body, international body, what we call as OECD guidelines for QSR model, already they mentioned detail about the model development process and what criteria should be there for approving the QSR model before submitting to approval of drug. So in OECD guidelines, they mention all 4 criteria, another 1/5 criteria they have included, that is mechanistic interpretation of the QSR model. So apart from 4 criteria, OECD guidelines approval committee required these 5 criteria for approval for QSR model. So you can just focus on these 5 criteria and try to develop the QSR model through any commercial or free softwares and try to develop the relationship model. In the first QSR model developed by Professor Hans, who is the professor of chemistry from Pomona College, California, USA. And Hans equation first time developed in 1969. And this equation for QSR basically relate the correlation between the activity with the hydrophobicity of the compound. So Dr. Hans first time relate the relationship and screen number of compounds. So log P is a chemical procedure or chemical descriptors basically indicating the hydrophobicity of the molecule. So log P should be like not more than 5. And this criteria is already covered in the Lipinski's rule of 5, where log P value should not be more than 5. So log P indicates the like lipid bilayer cell membrane nature and differentiate the values related to like solubility of the drug in octanol and water. If you see the schematic overview of the QSR process, you will be surprised that it starts with the molecular structural file information, which cover 1D, 2D, and 3D information within the file or within the structure. You can extract these information and then try to calculate the chemical properties, what we call as molecular descriptors. So there is open source software. You can use Paddle for calculation of molecular descriptors. So try to calculate properties like in this 5-6 categories, like constitutional descriptor should be there, electronic descriptor should be there, geometrical should be there, hydrophobic, lipophilicity, solubility, steric, quantum, and topological. So if you cover all these class of the chemical descriptors for a particular compound, and these compounds should be active in nature, then I'm sure you can able to extract the features which are responsible for the activity. And then go for machine learning data processing method using either normalization, standardization, feature selection, outlier detection. And in these pre-processing steps, you can use number of machine learning method. For example, do the multivariate analysis using multiple linear regression, self-organizing map, even principal component analysis you can do, even partial least square method you can use for model development. Even artificial neural network you can use to classify the compounds and develop the model. And even the support vector machine also you can use in QSR model development. And you can evaluate theoretically whether they are validated properly or not. You can use statistical parameters, evaluation parameters like correlation or regression or cross validation regression, even the error also, mean square error, and develop a graph which indicates the experimental activity versus predicted activity. So based on model development, you can set the filter criteria, what we call as AD. AD means applicability domain. And after that criteria, you can use this model for virtual screening of QSAR, QSTR, and QSPR model and predict the value of active compounds and classify the compound into active or inactive. So once the model is developed, you can screen number of compounds theoretically before wet lab. So this way you can save the lot of wet lab economy and time and resources. So what are the steps in QSR modeling? You see, it requires training set. Training set is an experimental data set where you have to like divide the training set into 80% for model development and 20% for testing. So 80% considered as model building training data set and 20% considered as a test set for the model validation. And then go for molecular property calculation. And then after calculation, try to select the only the key descriptors or very important descriptors which are not correlated with each others. So this process is called as descriptor or feature selection process, which requires correlation matrix, a principal component analysis, even collinearity analysis. And after feature selection, you come down and narrow down some selected chemical properties which are basically relevant with the activity. You can make the relationship with some machine learning method or statistical method. So normally PLS, MLR, ANN, artificial neural network, clustering method, or support vector regression is normally used for making the relationship between the compound activity and their chemical properties. And then we set the applicable domain for prediction and query set data evaluation and screen the molecule as active or inactive molecules. After theoretical validation and goodness of fit assessment, we normally predict the activity of untested compounds and screen the active compound for further wet lab evaluation through in vitro as well as in vivo assay. And after like in vitro and in vivo testing, we normally in parallel do the another ADME or what we call as PKPD analysis, electronic way or in silico way, some screening analysis for clinical trials indications like oral bioavailability evaluation through Lipinski's rule of 5 and in silico ADME analysis we do, in silico toxicity analysis we normally do, and number of properties you can predict nowadays with free softwares as well as commercial softwares. And after like identification of potential lead molecule with in silico as well as in vitro or in vivo testing, we normally do the molecular docking and AMD simulation on different targets or disease related receptors. We come down some binding affinity evaluation studies. And this way we can suggest the potential lead molecules and target for that particular lead molecules before approval or before clinical studies. So what do you mean by chemical descriptors? These are the numerical values that characterize the properties of a molecules, and it is considered that each active molecule has some structural properties inside which are not visible or you can see in naked eyes. So these information or uncoded information you can extract out through molecular descriptor calculation, and it requires a workstation or desktop for calculation of single or more than 100 to 100 molecules. So we normally consider chemical descriptors in 5 class. You can also follow that. Try to calculate the descriptors related with constitutional, electrostatic, topological, geometrical, and quantum chemical areas. You can use this software, which is also available open source, and it is used around 797 descriptors, and it is known as Paddle descriptor software, and it is freely available, and you can run on Windows and Linux in command prompt way. You can get the results. Another tool, it is freely also available in GitHub, is Moderate tool, but I suggest you go for Paddle only. This required this similar kind of properties. So general procedure already we discussed that in QSR model development, we don't go for detail. QSR method basically indicates the process of machine learning. You see there is a training data set which having some parameters, what we call as labeled data, and these labeled data with biological activity go for the process what we call as relationship modeling, and it requires prediction or classification modeling method of machine learning, where we use the test set, external set, and unknown query compound molecules to predict the activity of molecules. So this is a very general a process where required some medicinal chemistry and as well as some computational skill to come up with the good QSR model. And then you see in this slide, I just show you the calculated descriptor. It look like this one. The rows indicates the molecule name, and I think I listed 20 compound here, and around 1000 or 2000 properties considered initially for making the relationship. So these properties, or what we call as chemical descriptors, are in column areas, and first column indicates the like property or biological activity. So first column basically used for correlation purpose with other properties, and then try to develop the correlation matrix for feature selection. Those properties which have a correlation, high correlation or more than 0.5 correlation, plus minus, then you can remove these properties by seeing the table and only select those properties which do not having relationship with each other. This is called as collinearity test. So collinearity test required to remove the junk properties or unnecessary properties. Another method for feature selection is PCA, where high number of chemical descriptors are there, and we don't know which descriptor should be considered. So to narrow down the descriptors, we select PCA method, which convert the very large number of data set into very low dimension areas, or convert 5D plot into 2D plot. The aim of the PCA is to identify the pattern in the data set and detect the correlation between variables and to reduce the dimensionality and to find out the important features. So we normally use PCA in feature selection, even in compound selection also. So two parameters are there in QSR model to select the best training data set and to select the best descriptors or properties. And then you can use any method of machine learning to make the relationship. So PC analysis convert 6-dimensioning. For example, you see 6 dimension are there for different properties, and we select normally PC1 or PC2, 2 dimensions basically for best property representation. So this is the way to screen out the chemical descriptors which are having a control on biological activity. So this way we select the hidden properties which basically regulate the chemical property. And the advantages of QSR is normally in each lab in pharmaceutical company, QSR is very common method, and it explains the mechanism of action and indicates the properties which regulate the biological activity. It helps in prediction of biological activity. It also helps in understand the interaction between functional group and molecules of greatest activity with those with their targets. So you can use the QSR in different ways, but there are so many disadvantages of QSR also. So every method has some disadvantages. It gives sometimes false correlation. It gives indication that the training data set is biased and you have not covered enough training molecules in the sample. So number of molecules should not be less than 30. You should understand minimum 30 compounds should be there. Otherwise, it will give you the false results. So 30, 40 molecules should be there to make the relationship model. And then another normal error done in feature selection process where we do not consider the reliable properties and only predict some of the properties and take the some of the properties and make the relationship. Sometimes these 2D properties do not consider the 3D properties of the molecule. So 3D features are also required, and that is called as 3D QSR modeling. So you do after 2D QSR modeling, this is called as 2-dimensional QSR modeling. You can use the 3D QSR modeling also. There are so many application of QSR. You can predict the biological activity, prediction of chemical toxicity. You can do the environmental activity or toxicity prediction. So you can do the prediction of chemical properties, or you can save the wet lab economy and time spent in biological testing. You can also save the life of small animals used under preclinical experiments. So QSR having enormous benefit. You can use QSR consider as a prediction model. So model are of 3 types. One is prediction model, another is classification model, and third is optimization model. So normally in lead identification and lead optimization, we normally use prediction model and classification model. Optimization model basically used when you find the potential lead molecule and then you just want to increase the biological activity by manipulation or changing of some side change in the molecule. That is called as traditional SAR analysis. So the first priority should be identification of the lead and then go for optimization. Now we have seen the process, drug discovery process. Now let us see about machine learning methods. So machine learning methods application in feature selection and predictive modeling. Two areas we have already discussed. And what type of data required? You see in the diagram, I just tried to illustrate that earlier traditional programming considered only the data and program as an input and output delivered. But nowadays in machine learning, the input is input data as well as output data also. We provide the output data and train the machine learning model to predict some meaningful logical model or predict the alloc activity, for example. So you see the input criteria change now. Earlier, we don't provide the output. Nowadays, you have to provide the input data as well as output also. I mean, you have to like train the model with the molecule as well as their biological activity. Biological activity information should be there. Biological activity should be in the form of experimental activity, in the form of like IC50 or LD50 or EC50. So earlier programming languages do not consider the output, but machine learning method consider the input as well as output, means compound as well their biological activity, and train the model in such a way that it can use later on the results for prediction of model. In this slide, I just tried to list out the number of machine learning method you can use. Even you can write down. There are so many methods, but in drug discovery, normally we use 2-3 methods only. I just mentioned here, like we normally use machine learning can be of 3 types: reinforcements, supervised, and unsupervised. Supervised is again of 2 types: semi-supervised also, where training data include only few desired output. And supervised or inductive training includes the training data which include all the label data. For example, compound with known compound or drug with known biological activity. While the semi-supervised data include only the activity of few compounds and rest of compound do not have any activity reported. So that kind of data, I suggest don't use it in model development. Only use the supervised method where all the trainings data set, for example, I suggested you the 30 compound minimum. So all the 30 compounds should have biological activity. Then go for classification method first to cluster the authentic training data set and remove the noise data. So you can use the classification method. There are so many methods I listed here, like decision tree, Bayesian analysis, random forest, logistic regression, even rule induction method, instance-based learning method, ANN and SVM. While prediction model you can develop through regression analysis. So normally we use regression, linear, simple linear, multiple linear, non-linear also. So if the data set is very high, you go for non-linear. If the data set is less than 100, you go for simple linear or multiple linear regression. Another approach where we do not have any training data set and the lab is new one, department is newly established, do not have any experimental reports or experimental data in their record, and you just started the lab. Then the present day data with some number of compounds with their biological activity normally consider as unsupervised data, and we normally cluster it. And in clustering, we use a k-mean clustering or PC analysis or a hierarchical clustering or association method also. So we normally classify it and predict the model. So this is the overall machine learning steps, and each model development process follow this method where data collection, data pre-processing required, then model selection. You have to select the best model. You have to develop multiple model and select the best one, and then select the model training data set, and then do the model testing, what we call as validation. Validation is again two types. One is internal model testing, another is external model testing, external validation or internal validation. And then after validation, go for model tuning. Model tuning means fine tune or optimization, and then go for model prediction. So this is the basic step for machine learning model development. This is a diagrammatic representation where training set and test set you can divide. 80% is training set and test set is 20%, and try to develop the model of with the 80% data, where again two type of data category has been created. where dependent variables and independent variable classified and make the relationship and then develop the model. And this model is basically tested with test set and then try to calculate the error. After error, if less than 20% or 30%, normally 30% less than error consider for research analysis, and we go for publication of patent process. So machine learning algorithm basically has three components: representation, evaluation, and optimization. So representation requires these steps as listed in the slide. You see, you can use any one method: decision tree, set of rule, instances, graphical model, neural network, support vector machines. Based on your expertise or lab expertise, you can use any one method. Similarly, use one evaluation method at least. I listed some of the evaluation method, like try to identify the accuracy, precision, and recall, and squared error value, likelihood, or posterior probability. Do some validation purpose. So evaluation is kind of validation method. You should use some theoretical validation method and then go for optimization method. So last is optimization, which required greedy search, gradient descent method, or linear programming method. So this three step, if you have followed for machine learning method development process, I'm sure you will get the best model for screening. And I think you can screen number of lead molecules. So depend on the type of the learning, we can already define that supervised method is mostly used in drug discovery process, and other is unsupervised learning method where no data is there in prior reports. And semi-supervised and reinforcements, I don't suggest you. It is feedback basis development model. I don't suggest you. But supervised and unsupervised method are basically nowadays useful. And you see the list of the supervised method already discussed, listed here. You can use any one method. Now let us see the example of QSR model development and how to identify the model and check whether which model is best one or which model is worst. So you see the list of the molecules already listed through QSR modeling. And these are the known drug: metconazole, lombrezine, flubenazine, and norfloxacin antibiotic also. All are developed through QSR discovery process, and it is in market. There are so many other drug in market you can find out, even the natural molecules. So my work is on natural molecules. So I developed the galvanic acid derivative model, QSR model for immunomodulatory and anti-inflammatory activity in 2009. I think this is example where I selected some of the list of the known drug molecule on the top, and G1, G2, G3, G4, these are the derivatives of the galvanic derivatives with their predicted activity. We develop the model, and you see we find out 3, 4, 5 properties which indicating the LD50 value related chemical descriptors, and develop the relationship model. As you see, it is a mathematical model which is indicating the line equation model, y is equal to mx plus c. You see the predicted activity log LD50 and experimental activity is in linear fashion, and the model accuracy is R square value is 0.99, which is a well-known, good model, and cross-validation regression coefficient is also 96%. So 99% prediction accuracy of this model is well-known, reported in the published paper. You can see Journal of Molecular Modeling where this paper has been published. This is the second example of QSR model where we indicated the predicted activity and actual activity relationship. So the red dot indicates the training set, blue dot indicates the test set, and we identified 4 chemical properties in the contribution plot. You see in the right side top, contribution is of 20 to 40%, and these upper bar indicates the positive correlated properties, while the below 0 bar indicates the negative correlated properties. So these 4 properties regulate the activity of the training set. Training set is of 28 compounds. Test set size is 6. Because in natural molecule, the size of the training set is always small. We do not have much data. So whatever the data we have, we try to develop it and develop the model. You see the R square value is 89% and cross-validation equation, regression coefficient is 85%. So 89% model is good enough for publication and virtual screening of molecules, of natural molecule. So it very well predict the log percentage of inhibition value 1.94, which is experimentally tested or even checked in TRPV1 model, which is a calcium ion channel, basically, transient ion channel, basically, which has 1.972 value. So the prediction value of the predicted and experimental are nearby, and it indicates the training set and test set bar graph. You see another example where we see the overlap of training set and test set, and this model also include the 27 molecules, test set site 7, and R square value is 85%. You see and another model, we see the published data where you see the QSR model with IC50 value and prediction value of 85% R square value, and another model indicates the 98% R square value with the number of size is 26 and 36 molecules. This model is also published in Journal Molecular Modeling in 2010 around. Yeah. And this is the example of, this is another example where we use the machine learning method, what we call a support vector regression. And this uses the QSR model, which having the training data side more than 100. As I said, less than data, which is having a less than 100, you can use the regression method. And if the data side is more than 100, so you see in the text part, I mentioned that 2,291 compounds with the anti-breast cancer activity has been reported by Campbell and NCI and FDA, US FDA. So we covered 2,291 compounds. All these compounds basically having the good activity, anti-breast cancer activity. So we thought that all compounds have similar properties. We're surprised to know that these 2,000 compounds do not follow the same structural representation. You see, we first initially developed the clustering method, and we developed the clusters. Total 8 clusters we developed, and out of these clusters, we selected the centroid molecule. You see, the centroid molecule is of different type. So structural similarity is not the standard criteria. This method indicates that the compound structural properties are basically govern the similar activity, but not the structural representation. So this 8 cluster basically developed separately for model QSR model development. We developed 8 QSR model as listed in the table, and we use the molecules with the different models and predict the activity of GI50, which is a growth inhibition 50%. And this is also published in PLOS One paper. You can go for and see the detail of training data set, test data set, and clustering method and QSR method. So it uses the both classification as well as prediction model. Both machine learning method model used for identification of active molecules targeting against human breast cancer cell line MCF7. You see the clusters, 8 clusters are listed here, each cluster having similar centroid molecules. So all structures are not similar, but the beauty is that all compounds having a same activity, all are anti-cancer compounds. So this study represent the a research idea that the compound structure is not necessary. It is necessary to have similar properties. So internal property chemical descriptors are very much required for identification of mechanism of action of the molecule. This is another example where predictive drug likeness and ADME can be predicted through machine learning method, where we predicted the ADME properties of the xanthone derivatives, and it is already published in Drug Design Development Therapy Journal in 2014. You see, we classify the molecules, we develop the model with blue line bar, and green and bar is basically indicating the non-drugs. So those molecules which have non-drug properties, they are listed within that criteria. This way we can screen the molecules. And these are the representation of the ADME properties. We predict 4 properties basically. One is anti-cancer, second is mutagenicity, and third is anti-tubercular activity, and fourth is skin irritation. Another software you can use, which is called as Goosar, it is freely available. You can develop the QSR, QSPR model using your own data. For a student, I suggest you go through with this software. It is online freely available, and try to develop the model based on 2D chemical properties. This gives the result look like this one. And you can use a pre-developed model also. Another software is Laser, which also develop the model based on a structure activity relationship. And you can submit your own data and try to develop the model. And this is a bioavailability radar plot normally developed by Swiss ADME software, which is freely software. You can put your compound in the data in the web server tool and try to check whether your molecule fall within the red zone area or not. If it is crossing the properties of red zone area, which is an indication of drug-like molecules, so you can consider those molecules which fall within these properties: lipophilicity, insolubility, solubility, polarization, and flexibility and size. So these are the drug-like parameters normally evaluated for preliminary studies before clinical studies. Another beauty of this software is indicates the egg plot, or what we call as a boiled egg plot, which indicates whether your molecule lie within the ADME parameter or not. So you can check your molecule online, submit it, and check where example of anti-cancer drug you can use before comparing with your molecules. So positive control already always use, or some of the already known published known anti-cancer drug is already mentioned there. Select it for comparison and try to see whether your molecule fall within that category or not. These are the example of pharmacophore mapping, or what we call as pharmacophore modeling. And you can develop the model apart from QSR. You can develop the model through pharmacophore method, where 3D structure is required for the target as well as your drug molecule. And you can see the metabolism of these molecules through software also using machine learning method. You can predict the molecular docking, molecular docking based docking poses, where you can see the molecular dynamics of the molecule on particular target. So it look like this, like it mimics the cell in a box, and see the whether the molecule is reaching outside of the box or not. And you can see the inside of the molecular interaction where ligand and target showing the binding affinity. If there is a stable binding, the molecule will remain on the particular binding site. Otherwise, it will remove from the particular binding site. So I'm showing you the video where you can see the molecular dynamic simulation, which indicates the molecule bound molecules, which is a natural molecule, and this is a CYP protein, which indicates the enzyme. So you see the binding site pocket is within the same site, and the molecule retained within the binding pocket up to 100 nanosecond. So this is a 100 nanosecond simulation. You can show that binding affinity of the molecule on particular binding site. So this indicates this simulation result indicates the molecule is very well bound in the particular binding site, and this molecule is called as marinol. So this molecule is basically indicating the binding on CYP protein as a stable, and therefore we consider it as a potential binding site. So you can do this type of analysis through machine learning method or AI machine learning method. So there are so many server are there, even free softwares are there. I've done the simulation process through Gromex, which is freely available. You can set up in some workstation because it required a good course and CUDA course for analysis. These are some of the parameter of simulation where you can use it for evaluation of your molecule and compare with positive controls. So some of the parameter for MD simulation normally consider are temperature, pressure, and density comparison. And the simulation related or dynamics related parameters are RMSD, RMS fluctuation, and radiation of gyration. And the last parameter is binding energy evaluation. So interaction energy should be there. So you can plot the interaction energy also. So this also published in some journal. You can find the results in the references section. With this, thank you very much. Do you have any question you can ask us? Thank you.
Thank you so much, sir, for such an insightful and wonderful session. Our participants have the wonderful opportunity to interact with you directly. If you have any questions, you may ask.
Dr. Feroz sir, thank you so much for illustrative talk, and it's an thought-provoking talk, I would say.
Thank you.
Sir, so you have explained so many, you have given the examples of multiple tools which can be used in the drug design and as well as the development. So, for example, if there is any crude drug, so most of us in the phytopharmacy and phytomedicine and also in the pharmacology, so we screen the crude extract of the drug. So is there any tool which can help us in understanding the what kind of the activity may be there in the constituents of that crude extract?
For crude extract, we do not, because because drug development process basically for single molecules. The word drug is used for single molecules. In crude drug, we normally have multiple, because this crude drug basically used to develop the formulation, which in an extract form or some using the fractions. So it consider multiple molecules. So the criteria for identification of crude drug is normally based on crude drug based activity. So there is no machine learning or AI method for doing the such kind of things. Normally we use the HPLC or GCMS data to screen out the molecules based on activity. If the crude drug has the activity, there should be like some major constituent or minor constituent within that. Try to find out these major and minor compounds, and based on that, you can select, like for example, you found peaks for 10 or 20 molecules. So try to see which peaks are on high, which having the high concentration. So that peaks, which are basically maybe, for example, 5 or 6 compounds, they have in high concentration, you can consider as a major constituent, and rest of the molecule consider as a minor constituent. But you have to perform the molecular docking QSR study on these 20 molecules. So because you have already identified the molecules, these 20 molecules from the crude drug, so your input criteria should be 20, but narrow down to come out with some 4 or 5 molecules. You can use these 4 or 5 molecules under the category what we call as newly launched area or domain, what we call as new regulation for active pharmaceutical product development, what we call as phytopharmaceutical product. So you can club 2 or more than 2 compound with each other and try to evaluate the biological activity in vitro as well as in vivo, and go for phytopharmaceutical product development without clinical research. So it is easily approved by most of the pharmaceutical companies nowadays, which are working on Ayurvedic or Unani or other traditional methods. But the drug approval is not in the category of drug. All compounds basically considered as phytopharmaceutical constituent. So this is the way. For drug development, you need to go for clinical trials. And here, no clinical trials are done on crude drug or supplements or herbal formulation. I hope I clear the point.
Yeah, thank you so much, sir. Thank you.
Any other question?
Hello, good afternoon, sir. Sir, my question is, in
Good
spite
afternoon.
of 2D QSAR, is there any other method we have in AI, like through which we can be able to identify any compound within the minutes? Like if we will explore this compound for the activity, we can modulate its activity or not? Like in 2D QSAR, it takes a lot of time. And nowadays, people are not accepting research publication based on 2D QSAR. They're accepting papers based on machine learning. So is there any other method from AI? The software is freely available through which we can be able to get some compound and we can modulate its activity.
No. There are so many commercial companies, for example, Molsoft and San Diego, USA. They developed the QSR model-based software, which uses the machine learning and AI. And I forget the name, but the software name is, I think, ICM. ICM. Yeah, ICM from Molsoft, USA. ICM you can use for virtual screening of active molecules using the inbuilt QSR model-based models are there. So they uses the machine learning or AI approaches to screen out number of active molecules or for different activities. So based on availability of these model, you can screen it. But QSR 2D is very much required for developing the initially the relationship. Otherwise, there is another method I think which Dr. Ravi Shankar has been discussed, that rational drug designing approach that uses the 3D QSR approach also. But I think better is to do the 2D first and then go for 3D. And after that, you can use the virtual screening tool for screening of your own molecule. So without scientific intervention or relationship study, you cannot directly use the AI. Otherwise, a lot of drug can be approved in a day or 2 day or in a year. There is a no method basically.
Thank you, sir.
Okay.
Other questions? Okay, thank you so much, sir. Thank you so much, sir, for sharing your time and joining us today. Thank you.
Thank you. Thank you.
Now we will take a break for lunch. You all are requested to please join us by 2 p.m. Thank you, everyone. Welcome back, everyone. I hope you had a refreshing lunch. Let's now resume our workshop with the next engaging session. It's my pleasure to invite Dr. Rakesh Chandra Joshi, sir, from the Amity Center for Artificial Intelligence, Amity University, Uttar Pradesh, Noida, to deliver his talk on AI applications in pharmacy. Dr. Joshi is Assistant Professor at Amity Center for Artificial Intelligence, Amity University. His research focuses on deep learning, computer vision, biomedical signal processing, and edge computing. He has published 25 plus SCI Index journal articles and holds 2 Indian patents. He is an NVIDIA certified instructor and has experience working on multiple socially relevant AI projects. Additionally, he has co-investigated government-funded projects and served as an associate editor and reviewer for various journals. He is going to deliver a talk on AI applications in pharmacy. We welcome you, sir.
Thank you so much. And particularly, my talk is about the artificial intelligence-based application, and I will discuss 2 case studies in this particular lecture. So, initial slides will be particularly about the introduction of the AI in pharmacy, so this is some brief introduction, and later on, we will discuss what we have particularly developed in our lab and what we have particularly done with the different drugs over. So, we will see these things. This is particular our lab, so that this is the Amity Center for Artificial Intelligence, because if people are, you can say, promoting, that means they are using the AI or those part, but the necessary thing for any computer, you can say any institute, is the computing power. And we have a computing power of 10 petaflop, that means 10 into 10 to the power 15 operations per second can be done. So that means we can handle large amount of the data, and we have a high resource at our lab. That's why sometimes, because the drug-based works on where we have a large compute involved, so those can be easily feasible. That means that particularly with our hardware systems, and these systems are particularly from the NVIDIA. Particularly, NVIDIA is the largest company among all, you can say, at this time. So we have a largest turnover company, beating the Google, Amazon, all those companies. So we have this company called NVIDIA. So that means we have this company build up the GPUs, and all the, you can see the ChatGPT or these kinds of models we are coming in this space. All those are having the powered by the NVIDIA. That means particularly they are running on the hardware supplied by the NVIDIA. That's why this kind of compute is required for any system where you want to do such kind of research. Although we work on multiple number of applications over there, and these are some fields over there. In the right hand, in the left hand side, particularly you see that these are the particular models that are particularly used for different number of applications, and the second part is particularly where we are particularly working, and most of the particularly those I have shown multiple number of applications which are related to the healthcare and biomedical signal processing. So these are particular work which we are doing our center. So this is particularly introduction, particularly why we are using the AI in the pharmacy, particularly because nowadays because the people want to do the innovation and in the short amount of time, and the pharmacies, because experimental based and it is a lot of, you can say, time consumption is there. So based on this thing, audible or not? So what happens particularly because we want to do the fast computations and fast, you can say, experimentation. So AI is a kind of a boon in this era. So what happens with the help of AI, we can do large amount of computation, or that means suppose that you want to do, you can say, multiple number of experimentation over there. What happens? So suppose that suppose there are multiple number of drugs are there, multiple number of targets are there, and suppose that the combination is like you can say in 1 million. What happens? You cannot do the experiment for 1 million. Otherwise, if you took the experiment for 1 million, you can experiments over there, and you want to analyze those things. So it will very computing, you can say, computationally expensive. We have seen in the last, you can say, pandemic of the COVID. What happens? Because people want to develop a drug in a short time and do not have time to do the experimentation over there. So with the help of these kinds of AI tools, we can, you can say, select, suppose that out of those 1 million computations, you can experimentation over there, we can select that in top 100 computations, so top 100 experimentation, so that here we can do the, you can say just do the experimentation for those on only 100, which are, we can say, optimal, or you can say more, you can say, prominent. So for that experiment, we can do the things. Okay, that's why the particularly like you can say because R&D cost or everything, particularly they are increasing the cost, particularly because every industry moving towards the AI. Because even though they are, you can say, company in the pharma or in mechanical or every company over there, so they are particularly moving about the, you can say, pharma, so that they can analyze the, you can say, software over there, you can say, things over here. So I will show some innovations to you. That means particularly these are some basic things, particularly where what is the market cap of these kind of things. That means particularly it is going to be that $8.5 billion in the by the year 2030. So that means we have a huge, you can say, surge of different type of jobs. That means not only for, you can say, in the pharma sector, particularly not only who know the pharma, particularly who particularly integrate, or maybe some, you can say, proficient bio in the person capable of doing capable to do the bioinformatics. So we will do these kinds of, you can say, particular research over there, and the job market will be like the person who knows both the pharmacy and the AI. That can be a superior. So that for a managerial roles, particularly, he should know that particularly how AI, you can say, apply to those kind of pharma applications over there. And all these, because why you are doing this thing, particularly we have some kind of, you can say, in the, you can say, last point over there, you can see that means particularly we are talking about the GPU. GPU means graphic processing unit over there. Suppose that in a previous, all the, you can, computer that we are using, suppose this laptop you are using, it is a CPU. So because it is doing multiple number of operations. Suppose that we have 100, for any task, we have to do 100 number of operation, and one task takes a time of, you can say, 5 seconds. So then total time will be the 500 seconds over here. But with the help of GPU, we can do the task in parallel. Suppose that it can handle 4 tasks in parallel. So what happens? Suppose that for that time, suppose that for 100 tasks or 5 second time for each task, so total of 500 seconds, whatever, we can reduce it to the only of the 125 seconds over here. So this kind of GPU is there, okay? And the, you can say, the infrastructure, particularly for GPU, there are the server that we are talking in the initial slide. We have a capability of the 10 petaflop. That means we can handle a 10 petaflop. That means 10 into 10 to the power 15 operations and parallel. That means particularly in seconds. That's why we can compute. You can easily handle the compute this thing. Okay, and there is one, you can say, the name is written like AlphaFold over there. This is the model developed by the Google over there to analyze the protein structure of those things. That's why they have taken all the database from the PubMed and all the, you can say, repository over there, and based on this thing, they can analyze the protein structure, all those things. And few days back, I was also working with some, you can say, biomedical students. So she was particularly working on a fold analysis, because particularly you want to analyze the protein fold or those folds particularly. That means because how many number of folds are there and what is the pattern of the fold. So people want to analyze that in the protein structure. They can want to analyze those things. That's why the AlphaFold, particularly these kinds of architectures, that we can analyze the folds over there, and we can say that means which one is better. That means like because there are suppose that there are 8 like structure over there. So there are multiple types of 8 can be possible. Okay, and if you be surprised upon, suppose that if you are just you are tying up your shoe laces over there, the pattern of the, you can say, tying of the shoe laces, even the same tying same level, but sometimes you are having good strength over there, and sometimes having a loose, they can be loose. Okay, that means the fold structure is very much important in the context of the protein also. So this is the particularly, you can say, why AI is so much, you can say, in comparing to the traditional drug-based R&D industry. So why AI is so much powerful? Because we can do the things in very much fast. That means time efficiency very much fast. So that means we can do the large number of experiments, or we can say we can predict, that means which can be the optimal experiments after all the things. That means this is one part. Similarly, we can also do that means particularly that means we can save the failure rate particularly. That means suppose that you are doing multiple number of experiments over there, and many of get failed. And after the experimentation, after, you can say, putting lots of efforts and time on that experiment, you get to know that means particularly this experiment is not worthy over there. So that based on these kinds of, you can say, artificial intelligence based models over there, you can see that means which can, you can say, more efficient while you are designing the drug or those parts. So these are some basic, you can say, particularly, and similarly, that means because you are doing the fast work, and because these are the repetitive work, because you are utilizing the same GPU for a multiple purpose over there. That's why this is the cost saving. It is not like, you can say, pharma, particularly you are using some product over there and you are just disposing of after the experimentation over here, because you can utilize these kind of resources. It is a one-time investment over there, and based on the one-time investment, you can do the large number of experiments on the same device. So yes, I am talking to you. Particularly, these are some kinds. Particularly, people are using these kinds of models over there, and this is a particularly this is a unit of the Google, the particularly known as the Google DeepMind. They have developed this architecture like AlphaFold 3 over there. So it will predict the protein structure over there. That means what can be your optimal structure of the, you can say, protein over there, or because you cannot analyze those things. That means suppose that for a disease, what kind of, you can, protein structure you want to, you can say, check that part. So that means it can help with the AlphaFold 3. You can just Google this model, and you can say what is the capability of this thing. And it is like a particularly boom in the pharma industry, and particularly people who are working in the protein design or those things. Okay, that's why this is one part. And it has trained on the large machine, you can say all the resources available on the internet over here. So it is completely trained on all the related data with the protein. So it is, that's why it's so much powerful over here. Otherwise, we are also working on a generative chemistry models over here. That means we can generate multiple number of, you can say, data set over here. So that means whatever you are saying, particularly these are like a VAE, this is known as the variational autoencoder. This is like chemistry variational autoencoder. That means we have in our deep learning methodology, particularly we use this kind of architecture over there. But now we have integrated this kind of architecture for a chemistry purpose over there. That's why it becomes the CAM VAE. Similarly, this is the recurrent neural network, RNN. That means for your molecular, you can say, particular study over there. So we have analyzed these kind of structure over there. Like suppose that as we analyze the text, suppose that you have done the experimentation on a ChatGPT. That means you are writing some text over here, because it matters the sequence of the word. That means from after the he, that means you have put the is. From the you have put the R. Same like you can say any molecular structure or those things. That means sequence particularly matters over here. That's why whatever capability we are using for a text prediction over there, we are now analyzing those systems for a, you can say, chemical databases over there. Similarly, graph-based neural network, these are very much famous. That is particularly from last decade, people are multiple research have been done using the graph neural network over there. So that means you are, because such a particularly a graph-based structure are there. So that's means particularly we are doing this kind of research in the graph neural network. Particularly these kind of structures are particularly very much famous. Next one is the reinforcement learning agents over there. What particularly do, like when you teach your like small kids, that means how to teach your kids, that means this is the giraffe or this is the, you can say, you teach like this thing. Okay, similarly we have developed some kind of algorithms over there. Those are known as the reinforcement learning algorithm. So here we can teach, that means particularly this is the, you can show the data with a small amount over there, and model get intelligent after seeing lots of the data over here. Last year you have seen the huge market crash in the USA after the, sorry, few months back, I think so 3-4 months back. So there China have developed one architecture that is known as the Grok AI, particularly Grok. Okay, so what happens? The market got crashed, complete US market got crashed, because what they have claimed, particularly because whatever people are saying, that means we are developing a large language model and they are asking for you can say billions of the funding. So they have developed one architecture like a Grok. Okay, particularly that is having a very less cost in the development. So that means the whole market got, you can say, this thing. Okay, and that architecture is particularly built on these kinds of, you can say, methods like a reinforcement learning methods over there. So people now, instead of putting a lot of amount of data, model itself start learning the, you can say, bit by bit and become intelligent over there. So these are the methods over there. So these are some basic case study over there. That means particularly people do the antibiotic discovery with the help of a AI. So so these are, so you can say, multiple. That means the MIT, particularly Massachusetts Institute of Technology, particularly in USA, they have done the deep learning model that have there are 6,000 different molecules over here, and they have checked, I mean, whether they are, you can say, resistant to the, you can say, tuberculosis or you can say E. coli or not. That means particularly for different DJ, they have predicted resistance over there. I will show one case study, that means which we have done in our lab. So there we have done for a tuberculosis over there. That means they have done for 6,000 molecules over there. So that means that's why these kinds, they can find multiple now discovery with the help of the AI. That's why the main thing they are doing, particularly they have developed one architecture, particularly you can the sequence based architecture over there, and based on this thing they have analyzed the different property of the molecules over there and get the, you can say, results. That means whether the drug is susceptible or that drug is resistive to the, you can say, particular those kinds of things, and whichever you find resistance over there, and they can select those algorithms over there. Similarly, these are some studies over here, particularly that means particularly AI design drug in the trials over there. That means particularly we have a different number of, you can say, algorithms over there. So that means particularly like in the human trials, particularly it takes multiple number of months over there. So based on the, you can say, AI based mechanisms over there, they have reduced the, those trial to the 4 to 5 times faster. That means particularly so that if someone is taking in the 12 months of a time for a clinical trial over here, they have reduced the time to the, you can say, 3 to 4 months, because based on these kind of simulations over there, which is more productive or not. So these kind of people are doing these kind of study. That means particularly at the development of, in this slide, particularly that is for the development, at the time of development of the drugs over there, at the time of a, you can say, clinical, you can trial over there. So they have developing these kinds of development over there with the help of AI, because once you develop a product with the help of AI or those things, that when you can, because it can be in a software basis and you can easily replicate and you can test in the worldwide manner with the help of this thing. So this is a particularly drug development. I think so. Just I come to main slide first, and then I will come back to these things. Okay. Yeah. So particularly, what particularly all the slides particularly telling about that, particularly we have one work that we have particularly done, that is a genomic data and resistant modeling over there with the help of machine learning and deep learning algorithms over there. And please see, that means how we have done this part, and you can particularly understand what people, you can say other people are doing this thing. Okay. So we have different databases over there. That means we have a different drugs that we particularly use for TB disease. Particularly, we have a different drug like a rifamycin and isoniazid. These kind of, they are 4 drugs over there, and we have analyzed different number of, you can say, genes over there: RPOB, INHA, CATG, PNC. Maybe you know particularly better than us. So these are the particular things over there. Okay, and we have based on these kind of pattern from these kind of 2 databases like GMTB and TBD, READ, MDB. So we have from these databases, we have collected multiple number of things, and multiple number of, variants are common, so that we can identify for this RPOB, we have identified 114 number of unique, variations are there. So based on this thing, we have in which those variations, 50 were the resistance and the 64 were the susceptible. So we have collected the data for multiple number of genes and the drugs over there. And the main purpose of this research was to develop a mechanism so that we can put the, particularly gene or drug-based combination over there, and we can we want to predict that means whether the combination will be, resistive or susceptible over there. So we have done this study. So these are the database statistics are there. So what we have particularly taken the characteristic, because to do these tasks, so what we have done, particularly we have done some kind of numerical features and some categorical features over here. So for numerical features, we have taken the molecular weight, the volume particularly, and polarity, isoelectric point, hydrophobicity, and normalized accessible surface area. So we have analyzed this thing, and we have access through the some, mapping from the IIT Madras database. So we have done this part. So that means particularly there are 6 numerical features over here, and there are 3 more categorical features over here. That means residue type, like a wild type, mutant over there. And so these are some naming over there. That means particularly some are aromatic, some are polar, some are charged over there. So we have done into hydrophobic are named as a 0, and then aromatic are putting as a 1, and we have done this part in a categorical manner. Similarly, we have also checked the secondary structure over there. That means which are the helix, seed, turn, coil. So we have done this part over here. That means to make this prediction happen, that is particularly whether this resistance or not. So we have taken these kind of features, like 6 features of this thing, and the particularly 3 features of categorical features over here. Based on this thing, we have developed one architecture over here. Particularly, this is the particular block diagram for this thing. It is not published yet. It is a submission stage. So in this thing, we have done the same thing. That in particularly, we have done the numerical data over here. In the hands-on session, I will do the experimentation on this kind of data set over there. So that means how to handle these kind of data, where you collect in the Excel sheets over there, and based on this thing, how you can make the predictions over there. So we will go for different, drugs, and also the when I think so one disease also. I think so I can do for Alzheimer also. So we can do those parts. So see, these are different type of features over here, and based on this thing, these are numerical features, and we have some categorical features over there. Based on this thing, we are doing some kind of converting into numerical form over there, and then we have developed one architecture. This is a little bit complex architecture. That means particularly because to analyze these kind of things is not, we have tried simple architecture over there, but we are not getting very much high accuracy over there. So that means we have developed our own architecture. So that means there is one architecture that is particularly built on the, graph convolution network, or as last I have discussed, that is graph neural network particularly. So we have developed this architecture one part, and we have done the transformer part. Whatever you are saying, that in particular GPT, BERT, these kind of models are showing, the last word is T. The T is showing the transformer. That means particularly all the architectures are powered by the architecture that is named as the transformer architecture. So we have developed this architecture, this thing, and based on this thing, we have made the prediction of this tuberculosis resistance over there. So this is a particular architecture. That means we have multiple number of layers, and we are dealing with the numerical data and categorical data. And based on this thing, we have made the predictions over here. So we got the best accuracy for 10-fold cross-validation. We got the 97.152% in the architecture over here for this task, and we got the very high precision for this thing particularly. So this is a particular, you can say this thing, and we have, because we have done the evaluation study for this thing. That means we have using a multiple number of blocks over there. So whether the combination of this thing or this thing, or we have analyzed multiple number of pattern over there, and we have checked that means the best outcome is the complete model over there. So we have done this part. This is the Campion matrix. That means the 75 out of the 75 are correct, predicted correctly for a susceptible purpose, and for a resistant purpose, that means out of 76, 74 prediction done correctly. So this is the analysis that particularly, that means particularly we have analyzed what is the feature weightage for that thing. That means hydrophobicity has the higher weightage, and then the molecular weight, then isoelectric point, then normalized ASA. So these are the, you can say for making a prediction, this is the priority of, you can say, different number of features over there. These things are analyzed by the model itself, not by us. That means just we have put the data set over there, we have organized data set, and we have developed the architecture, and all the analysis done by the architecture, and based on this thing, we can do the thing. Okay. Similarly, similar study can be done for you can say for a TB study, for like this we have done for a TB. It can be done for other disease also. That means particularly we have to check the drug database and the gene database over there, and we can replicate this study over there. Because I am having a not much background about these kind of things, so it take me 2.5 years, particularly discussing about a lot of scientists over there. That means particularly from, because so I have started working on 2020 over there, then stopped that work, then started again and again, because these kinds of like resistance susceptibility are very new to me. So that means it takes a lot of time. That means that's like, so if we can make some kind of interdisciplinary study, so that means you can use your expertise, I can use my expertise over there. So we can design more accreditation in a more faster way, so we can have more impactful. So next one, the work which we have done for it is the binding affinity prediction over there. So particularly people do multiple number of tasks like a drug target interaction, or they want to do drug interaction over there. So because it involves large number of experimentation in this case. So to reduce the number of experimentation and reduce the computation cost and time, so we have developed one other architecture. Here I state this in this work. So this was work done by Vinay Priya Mishra, particularly the another, you can say, researcher. So which we have done, particularly the prediction of the binding affinity. So there are multiple number of tasks. Generally, if you search for that thing, generally one is the DTI, drug target interaction, and another is DDI, drug interaction. So we have focused on the DTI particularly. So for DTI particularly, because large number of, you can say, in this study particularly, we have a multiple number of drug compounds are there, and we have a multiple number of target molecules over there. So to analyze those patterns over there, so we can analyze this thing with the these are just you can say particularly it take a time consuming, or whatever I've discussed in the last slide, I mean particularly time consuming and takes a lot of time. And generally, although analysis particularly which people done in a traditional method, they use the 3D information over there. But in this work particularly, we have analyze only the 2D information. And based on that 2D information, we have done the complete analysis over there. So instead of a 3D information, because so that's why this work is more impactful as compared to, you can say, large requirement over there. So in this thing particularly, so we have taken the chemical structure over here. That means you have sequential representation of the chemical over here. And based on this thing, we have developed one architecture. These are, you can say, particularly known as our function like convolution neural network or those things. So these are our, you can say, time series analysis networks are there. Now we have done this experimentation for the pharma domain. So particularly we have done these kinds of, you can say, strings over there, small strings over there, analyze those patterns. We have converted, they are in the textual format over. We have converted those things into the numerical form. And based on this thing, we have passed through the multiple, you can say, sequence of the layers over there. And based on the thing, we can get the prediction. In our AI terminology, particularly this task is known as the regression task. That means the classification means, that means the last task which we have seen, that is a classification, that is known as a binary classification, because we are classifying the data into the resistance and susceptible category. But in this case, we are predicting a binding affinity. That means a score, that means numerical value over there. So that's why this task is known as a regression task in our particular in AI terminology over there. So we are doing for a regression task over here. So these are, you can say, particularly we have taken the multiple number of Kiva scores and smiles or these things. I think so you particularly know better than us. Particularly we have synthesized this data set over there, and based on this thing, we have put this data set into a structure form, and based on this thing, we have gone to the data set. So you can see the particular chain of the sequence over there, particularly. So we have a drug protein over there. We have combined the SMILE and protein sequences over there and divided into the train and that means 70% data for the training part and 30% data for the testing part. And then we have passed into our network over there and then we got the outcome. And the outcome is particularly numerical outcome over there. So we have computed into the two scores over there. One is the mean square error over there and next one is the concordance index over there. So we have analyzed in two terms over there. So this is a complete, you can say, architecture of this thing. Particularly, we are analyzing the drug-based part from one network over there and protein information from the second network. And after processing through those layers, we are combining those information into a single network. And based on this thing, we are predicting the binding affinity of the model. So these are the complete, you can say, learning curve for this thing. That means first one is showing that means concordance index is going higher and higher. And similarly, the you can say loss is getting lower after multiple number of iterations, or you can say particular epochs over there. So we have done this thing, and whatever we are seeing this block, these are the hyperparameters used for this research. So particularly people are using for multiple number of things over here. So like a molecular docking or deep learning model. So what happens? These are molecular docking are, you can say, a programmed software over there. That means you have put the instruction over there and based on those instructions, it is doing all those tasks. But the deep learning has its own thinking capability. It can make the predictions over there. So that means the decisive capability is in the deep learning neural network over there. So that means if you want to make more decisive network, decision system over there, so you can utilize the deep learning models in your applications over there. So we have working on nowadays I am working on a fold structure analysis over there. So I have studying the, you can say, particular rope-based structure also and protein structure also. So that we are developing, that means how can we analyze, that means identify different number of folds in the protein structure. So I am doing that research nowadays. So these are particular two case study particularly, which if you want to ask any particular question about architecture or those why, particularly you can ask the question based on the, you can particular this kind of mechanism that we have done instead of this particular this part and this part. So because the domain knowledge is particularly with you, but particularly the architecture part that we have done particularly for this thing. So we have done this part. So because multiple number of applications are there, what I have came across a hurdle while doing this kind of research over there, because you have some kind of gene database or those database, so you have to go one by one and to analyze those parts. For us, that is very much difficult because to analyze those, because when we see those kind of pages over there, we have lots of strings are there, those things that we could not able to identify. That means which one is more useful or those things. That's why it take lot of time to us. So if you can help on those kind of, you can say structure up, you can formulate the problem over there. So it can be more useful and you can say we can give more impactful research over there. Otherwise, for us, for any pharma or any, you can say any other domain, we have you can like it acts like data also, because we have you give the text data, you have to give a tabular sheet, you give the images. So that means all act as a data to us, and we have a particular network with us. We can design our network, and based on this thing, we can make the predictions over here. So after lots of struggle, we have come to this kind of study over there because we have done this thing independently, and some sessions from the, you can CDRI, Lucknow also, and some institutes also. So these are two works that we have shown you. So particularly, so this one particularly from my side, particularly that means particularly AI booming up, particularly, but what I particularly think that means if good interdisciplinary, you can say work can be done with the AI people and the, you can say pharma people, so it would be better, better at this time. Because it is very much tough, because for other domains, suppose if you are I been doing the, you can say radiology image analysis or any those analysis, it is very much simple for me because I go to they put the data into the simple folder over there. That is very much easy for me. But for analyzing this kind of data, it will become very difficult. I cannot do these kinds of work very much independently. So that's why the collaboration is very much important for this class. I will do the hands-on also. That means what I have developed those things. So how we are analyzing data, how data look like, how put the data, and how we run in the Python over here. So we can see in the lab. So we can do that part. Which graph?
This one, the fully connected dense layers. So is it an agent AI or what is this?
No, simple AI, simple AI.
Simple AI.
Yeah. What happens, particularly in our terms, like I'll give you a simple example. Like these are the different connections over there. And in our language, these are known as the weights and biases. What are these? Particularly, suppose that I want to count the number of people in this room. So I can count 1, 2, 3, 4, 5, 6 over there. But my eyes are seeing everything. That means I am seeing the chair also, table also, the thing. But for a particular task, I am focusing. That means particularly 1, 2, 3. That means I am focusing on the people faces over there and ignoring all the information. Even though because I am doing with my brain, I am not putting any much effort for this thing. That's why I am ignoring everything. That means in our language, it is known as that means I am putting more weightage for a person faces and I am putting less weightage for the other information over there. And these are the connections over there. That means you are putting the data over there. And for the different connections over there, I have connected with the chair also. I am connected with the person also. But for this task, I am getting the higher weightage for, you can say, people. That's why these kind of networks are there. And what are these? These are some numerical value, like ranging in the 0 to 1. Like a probability value, like if I did 0.9, that means I'm giving higher weightage. If I did 0.1, that means I'm getting the less weightage. So this kind of architecture are, if you are doing from a very traditional, you can say conventional AI to very, you can say recent AI. So all these architectures are very much common, and this structure is very much common in every, you can say, architecture over there. So these are the weights over there. That's why in this side you are putting the data over there, but where I have to focus, what amount of focus I have to do those parts, it is learning through these kind of networks over there.
Okay, so thank you.
Yeah. Just AI, what AI, particularly AI, that means if you show lots of example of any of the, you can say, combinations over there, if you are doing those research, you can say related data over there, you can check for the other also. If he very much new, that means you do not have any yeah. Okay. That can be tough if you related to any of the things. Otherwise it will be tough. Okay. Yeah, no. If suppose that there is no research done on the Mars over there, if somebody ask the question on Mars over there, so but what happens? AI give the answers. In our language, it is known as hallucination. Maybe if you can ask the question like a MET or those things, you can say ChatGPT or those parts. What happens? It can able to answer those parts. Okay. But what happens? Sometimes it gets hallucinated. Because when ChatGPT came, people started writing a research paper or those parts over there. Now people see that means how retraction rate is very much high. Because the referencing or those things, they got the output from the ChatGPT. They completely relied on that thing, but the research which they have cited never existed at that part. That's why this thing. That's why the reliability of the AI, particularly you can say for new, you can say any domain that have very less research is done. So that can be doubtful. So that can be, if you have a sufficient amount of data. So but nowadays people are working on some techniques over there. Those are known as the zero shot learning and a few shot learning. Zero shot learning means we have in few days back we have discussing one work over here. So what they have done, particularly they have trained the images of the horses, okay, and based on the text or those things, okay. But now after giving the text and those information, they can able to predict the image of the elephant. They have not shown the elephant to the, you can say, model over there. Just they have put the image over there, but based on the text similarity or the semantics over there, it can able to predict that means this animal is this is the elephant over there. And in our term, it is known as zero shot learning. Maybe in after you can say few months or few years over there, maybe we can become more capable and we can do this kind of research also. So people are working, not kind of pharma, not much aware about that thing, but people are working, and the particular terms are pretty known. That is zero shot learning. And some research are doing a few shot learning. That means you have shown few instances over there, and based on this thing, you can ask in a question. In ChatGPT also, particularly you are writing about your some data over there, few shot. That means particularly putting this thing, and you can able to ask the questions over there. So we can do that part.
Yes, sir. Thank you for this nice presentation. There is one concept in the treatment, that is the risk to benefit ratio. For treatment of one disease, we have option of 100 of the drug molecules available, right? So risk to benefit ratio is that, for example, if a drug like anti-cancer, it will have side effects for sure. But the benefit is that we have to save the life of the patient. So is there anything, any parameter in your AI which can determine the risk to benefit ratio to select the best possible drug for the treatment out of various options available.
Particularly not about whatever you are talking, particularly field, I have no knowledge, but I can give you the idea that particularly how can we solve this problem over there. If you can do that, means you can easily solve that problem. Particularly suppose that you want to predict what you have said, particularly
Risk to benefit ratio.
risk to
Actually,
benefit.
for safety parameter, they are in the docking. We can
I have done
ADME
for
studies can be done. But for risk to benefit ratio, is there any parameter which can be studied through AI? This I want to know.
Definitely. If you can represent your data, like I suppose that because what I have done for a binding affinity over there, just I'm predicting a numerical number over there. For in this case, that means your benefit to risk ratio, particularly that is numerical number over there. If I give the data in some, suppose that for any patient data or whatever the drug data or I am giving to you, if I can represent into the multiple like a structure pattern over there or those you can say molecular weight or those kind of pattern, I can give those data. So I can give the for 100 number of patients over there, and based on this thing, I can make a prediction for a 101 patient over there. So that means whether what will be the you can say the risk benefit to risk ratio. So I can make the prediction over there. Just we need to represent that input data into the multiple number of you can say values over there. In our terms, it is known as the features over there. If I can make the extract those features over there, if you can give the data to us, so we can do the same task. No issue.
Thank you.
Congratulations for those innovative novel works you have done so far, sir. I would like to ask, you said that in order to train your models, you put large number of data inside. Where do you get these data from? It's also predictive or the real scenarios?
No, but completely real scenario over there. They are hosted in the public domain over there. So what they have been given to us as particular data over there. Sometimes the complete data is hosted on the web over there. Sometimes the partial data. Suppose that they have written the name of the gene over there, and I have to go to the you can say IIT, you can say Madras Laboratory or those things. Okay. So I get the structure property of that. So generally, in pharma domain, that is very much less than the complete data is in one place. But for other domain, particularly, they put the data like suppose that I want to do the you can say prediction like suppose from a chest X-ray images, I have you can say what is the TB, bacterial pneumonia, viral pneumonia, COVID. I want to predict that from that thing. Then putting the single probability that is easy. But for a pharma domain, they generally do not keep the complete data into a single thing. Maybe, but I could not find. Maybe I'm not. But you can make a prediction with the help of those things. So generally, not large amount of data. Sometimes some good amount of data which is high estimated over there, we can able to learn the pattern over there and get the things done.
With the small data, you can augment it with a kind of an prediction model.
That's very much higher. If I'm doing like you can say I'm just predicting like a bacterial pneumonia, viral pneumonia from radiology data, which is already available on that thing, so that value less as compared to those kind of things where I have to struggle for the data to point out the data and to make the data over there. So that value is more impactful as compared in these days particularly. So as such kind of labs are very much less in India. That's such.
Okay, sir. Until now, you worked on drug discovery. What about the preventive methods, like prevention of a disease?
So for that, we have done the other work also.
Have you worked on the preventive?
For multiple number of disease, particularly we do for a study purpose. Particularly we I think so. Sir, I've given the lecture particularly in the morning. I think so. We have shown multiple number of things over here. So we have developed a multiple number of diseases. Some of them like a cervical cancer, particularly based on the you can say socio-demographic data and a gene data, we can make a prediction about cervical cancer so that we can avoid, because particularly in rural area, they do not have a you can say facility of those kinds of you can say high research instrument over here. But based on that thing, just you can make a socio-demographic data, you can make a prediction over here. Nowadays we are working with the ICMR NIH Chennai lab, particularly. So here what we are doing, particularly we are doing a symptom-based prediction for a virus. 40 different viruses like a dengue, chikungunya, hepatitis A, B, C, D. So particularly for these viruses, we are just putting a symptom. No blood-based biomarker, no anything particularly. Just based on symptom, we are making prediction. For that thing, we are getting the accuracy. Like top 1 accuracy is 71% and top 5 is 97%. What it means particularly, we can out of 40, we can make the prediction correct out of the top 5, and then 97% over it based on symptoms. What the impact of this is particularly, we can reduce the, you can say, generally what happens, you go to the doctor, it says multiple number of tests over there. After doing multiple number of tests, whatever you came to know, that means these things are negative and only 2 things are positive over there. So for that thing, it consumes the time also. Suppose that you are going in the live threatening condition over there, it consumes time also and cost also. So we can reduce that thing with the help of that method also. All are in preventive manner, and we have collected for that mechanism. We have got a data set of the 40 lakh people data. Because we are working on VRLDN network over there. In all over India, particularly they have for any hospital, they have associated with the there is some unit over there which is recording the whatever test is done, what is the outcome of those tests, those things done over here. So we have database of 40 lakh people over there. Now we are updating for 2 years also. Maybe we can extend it to the 60 lakh over here. So we are working on that thing. All are in the preventive manner particularly.
Okay.
Means we have done multiple more things, particularly for a like a retinal, you can say retinal disease, that means we can able to predict the glaucoma or a diabetic retinopathy in earlier stage. So that means you can take a preventive care. But that means what is the main issue particularly? People got to know like a cancer or those things are in a very later stage. So we have developed multiple algorithms so that we can detect those things in an earlier stage. Like we have done for a glioma also, that is particularly for brain cancer. Particularly we can detect it in an earlier stage, we can take a preventive care also. But particularly not, we have particularly targeted the rural population in our aspect particularly, whatever we have developed, particularly for a rural population, because they do not have access of those resources. We have done that part.
Oh, congratulations, sir.
This is for the part.
That part is really surprising because all the viral infections will show the symptoms, especially when you talk other than the biomarker, only the symptom, it will be the same. I think so. Like a cough, the cough flu-like symptoms, fever, along with anti-inflammatory reactions. So, but in that, how you can able to segregate out of the, that is surprising. Other than the biomarker, especially you said that. So we'll just talk about that, sir, when time permits.
Just see, for that thing, particularly fever, we are talking about fever, that is very much common. Your dengue, that is also fever, chikungunya, that is same fever, and particularly for dengue and chikungunya, symptoms are completely similar, almost. So that means you can make a, that's why we have taken multiple number of things. That means that we have taken a straight name also a category over there, or particularly age category of those time, so that sometimes so that because these kind of viral diseases are season dependent, particularly like in the rain or those parts like that. And what happens? Suppose that June and July month is raining for our Noida over there. Maybe for a China it can be different months over there. So that means state level data mapping over there. So we can do that part. That's why this can become a more some discriminating features over there, and we can be able to do. That's why the top one accuracy, if you see top one accuracy, that means just final prediction at a first instant. That is only 71%. That's all.
That's fine, sir.
Thank you so much, sir, for such an engaging and thought-provoking session. Now it's time for hands-on training session, which will be conducted by Amity Center for Artificial Intelligence. This session will include practical demonstration and a discussion on possible research problems. So I request Dr. Joshi to please lead us for hands-on training session. So we will move forward to E3 block G16. Thank you. All the participants who have joined online are requested to please be online. We will resume shortly from the AI lab.
E3 में वाला है। हाँ मीटिंग क्लोज नहीं करेंगे, मीटिंग करेंगे बट ऑन करोगे। Okay, we'll go to E3 now.
Hello, good evening, everyone. So I can see Pratibha. Dhanlakshmi ma'am, good evening. Is it good afternoon or good evening? Okay. Dr. Dhanlakshmi has joined from Oman. So she's from National University of Science and Technology, Oman. So thank you so much for joining us online, and I take this opportunity to thank our founder president sir for creating such a wonderful facilities, and Dr. and our honorable chancellor sir, honorable vice chancellor madam, and uh, additional pro vice chancellor Dr. M.K. Datta sir. Uh, I also thank our speakers for today's session, Dr. Uh, Ravi Shankar, Dr. Feroz, Dr. Rakesh. So thank you so much, and thanks to all the participants for enjoying this day. And this is an quite exciting journey we had today. A lot of things we learned, but we cannot learn everything on one. So it requires some time also. And as there are some questions from Dr. Smriti and as well as Dr. Annie and Dr. Hemlata ma'am and Dr. Indu also. So it is important to in the drug discovery is not so easy. That's what he said in the morning, Dr. Shiv Prakash. It requires the team of the people. And currently what we use the software that is a Sronizer that could help us in predicting some of the important component of the chemical molecule, and then we can take it forward. But here in the artificial intelligence and machine learning, so Dr. Feroz has very well illustrated how to find out the drug affinity and other things. So I think so it requires some more time to work upon and learn more and more, and that can be done only by one-to-one interaction. That is what our Professor M.K. Datta sir has mentioned. So you bring a problem to the AI Amity Center, and then you catch a person like Dr. Rakesh and sit with the one or two persons and then make them to understand. So what is your problem? So once they understand the problem, then they'll try to find out the solution. But the solution will not come from their side, it will come only with your participation. So because he will understand on the one side, but the holistic approach will not be there. The global approach will not be there. Like for example, if a drug is found to be effective, but if it is not safe, then it is not no use. So if a drug is quite good in treating your cough, but at the same time, if it is damaging your lungs or if it is causing the asthma or allergic reaction, then the drug has no use. So therefore, it is important for us to sit with the AI specialist and also the ML specialist and make them to understand and try to find out the solution for that. And I'm sure so that will give the sufficient support to us for the new drug discovery. But what Dr. M.K. Datta sir has mentioned, so he has shown some of the models like osteoporosis prediction model. Then we have the malaria prediction model. So these are quite easier one, I think. So our pharmacology students can work upon this project, and even the pharmacy practitioners can also work. So because the slides, histopathological slides, if you take, so the liver will remain the liver. But if there is a fibrosis or if there is any necrosis or if there is any inflammation, so the histopathological slides will show. But again, the challenge comes, so which part of the liver you have taken? Like for example, if you take this section in the central portal vein, so you will see this something different. And if the section is taken at the peripheral vein, the histopathology will differ. So therefore, it is also important for us to be more precise. That is what Dr. Porsalvi madam has raised that issue. How precise your result is and how accurate it is. Like even if you twist it and the portal vein is not taken, the histopathology is not taken from the portal vein, it is taken from the peripheral vein. And even if you twist on the left side, right side, ups and downs, but that is an error. So that error could be existing in your data system. So that's why what Dr. Rakesh has mentioned, you require the more data. So as much as the data you have, as much as the patients are involved, that much more reproducibility, that much more accuracy the prediction would be. So therefore, it is the easiest way to start the AI integration in the pharmacy, MIT Institute of Pharmacy is the door opens from Dr. Prakash Haloi. So it goes like this straight, and then so you can use it for the prediction. So if we have a lot of the skills, as Dr. Rakesh has sir and MK Datta sir has shown, the prediction model, the risk factor risk. So there are so whether you smoke or you drink or you take milk or you do not take the milk, so you eat egg or not eat egg. So there are the scales are there. So if these scales are used and then you start collecting the data from the patient and then start using these prediction models. So that can help you to publish the papers in the good journals and also develop the good applications, also mobile applications. And I think there's a long way to go with the MIT Institute of Artificial Intelligence, MIT Center for the Artificial Intelligence. And definitely we are looking forward for the collaboration, sir. And I'm sure so we'll have some good collaborations and the outcomes of the collaboration also. At this time, so I would like to take a special opportunity to thank these two research scholars from the Banasthali Vidyapit and coming physically and participating in the event. And I'm sure so you have learned something, right? But so the one day learning may not be sufficient, but it is just an orientation, right? Which we call it a shadowing. You get shadowed to the AI system in the healthcare, and then you keep on learning and learning. So then you will develop this certain good system. So at this juncture again, before I conclude, I would like to thank these young boys and as well as the little younger one, these boys and all the girls for participating in this event and making this workshop successful. Thank you so much. Thanks to all the participants. Thank you. So then we close this event. Thank you, sir. Thank you so much.
PhD from Singapore.
No, our institute is particularly in Center for Advanced Studies. रोड के साइड से सीढ़ियाँ है ना पर लखनऊ में बस बस बगल में एक है आपका सीढ़ी में सेंटर पर एडवांस स्टडी क्या होगा
अच्छा जो अभी जब सीढ़ियाँ इधर शिफ्ट हुआ
हाँ नया वाला पहले तो आपका सेंटर बता आपका वो लखनऊ सेंटर बता आपका अभी यहाँ पर जांगी में
I will be updated.
Sure.
तो कहाँ बैठते कहाँ?
See first floor पर 102 पे है E3 पे.
Thank you.
Some